the session, I just want us to recap or remind ourselves of what vertical projectile motion is and what exactly can be accompanied or be found with vertical projectile. So we know that if, let's say, an example, if an object is thrown out of the window, maybe a frog that is jumping or a ball that is being kicked around, all these can be regarded as examples of vertical projectile or basically projectile motion. So in most cases, they tell us that we must ignore the air resistance or the friction that is taking place within the space or within the direction of motion, so that our calculations can make sense. So there was a gentleman by the names of Galileo who made a study about vertical projectile motion, and initially it was just believed that when you throw something, it must just come back straight to the earth as long as you've thrown it, let's say, upwards. Okay, according to this gentleman, he believes any object that is thrown upwards or dropped or projected must always take some sort of a curve, sort of directional movement, which means that this object must have two components: the horizontal component and then the vertical component. So when we talk about vertical projectile, our main focus is basically the vertical component. Okay, so in all of this motion is affected mainly by the acceleration due to gravity, which is 9.8 meters per second. Okay, so we're saying at the same time the projectile can move horizontally according to the principle that this guy discovered. And then when we look at the combination of the vertical and the horizontal, that's when we can get the actual resultant projectile motion or graph. Okay, then what other thing that we need to also talk about will be the definitions that we normally come across, the terms or terminologies under vertical projectile. So number one is what we call the free fall. So any object that is acted upon by gravity. So any object acted upon by gravity is believed to be under free fall. Acted upon by gravity is said to be under, let's say, state of free fall. State of free fall. So in other words, this is motion that is entirely influenced by acceleration due to gravity. And then terminology number two, we can talk about a projectile. What is a projectile? So a projectile is basically the object that starts, an object that starts its motion. An object that starts its motion with basically an initial velocity. Okay, this does not mean that the object has to be just thrown upwards, or it covers everything. It can be thrown upwards, it can even be dropped, or any other scenario. And then we have what we call a trajectory. So a trajectory is basically the path that is followed by a projectile, or the path that is taken by a projectile. That is a trajectory. Okay, and then number four, we have the terminal velocity. So terminal velocity is more like the maximum velocity that is reached by a falling object. I'm just gonna summarize it and call it maximum velocity that is reached by a falling object or object under free fall. And then free falling objects, we said they are mainly influenced by acceleration due to gravity. Okay, so under vertical projectile, we have what we call scenarios that we're gonna focus on. Okay, we can I don't know, I'll call these cases. So the first case is where we find an object thrown upwards. object that is thrown upwards. That is scenario number 1. And then what happens in that, what we need to know, we shall discuss that. Then 2, let's say this is thrown upwards, let's from the ground. Okay, and then scenario number 2, an object that is thrown upwards but from a certain height. Same scenario but from a certain height. An example, you stand on top of a tall building and then you throw something up. What happens? That will be like scenario number 2 or case study number 2. Then we also have case study number 3. And this case study, we look at an object that is thrown downwards. Object that is thrown downwards. So in most cases, from a certain height. From a certain height. An example, a platform, a cliff, or even a balcony. Okay, that is thrown downwards with some bit of velocity, whereby the initial velocity is not 0. And then number 4, what if the object is just released? Object is released or just dropped from a certain height, whereby the initial velocity is 0. That is case scenario number 4. And then lastly is case scenario number 5, an object that is released from a moving object. Object released from a moving object. An example, if you're in a hot air balloon that is moving upwards and then you drop something. So whatever object you've dropped is gonna possess the initial velocity. That will be the velocity of that air balloon. Okay, then the other thing that we also need to familiarize ourselves with is the Newton's laws of motion. Okay, we have quite a number and we just need to be really selective in which one to use. Newton's equations of motion. Newton's equations of motion. Okay, so we know that first equation, which is V final, is equal to V initial plus, you can say, acceleration times delta t. But in most cases, we're not gonna call it the acceleration. In this case, since the object is under the influence of gravity, that acceleration A is gonna be turned into the gravitational force, which is G. So in other words, it's gonna be V final is equal to V initial plus G delta t. Okay, where the G is gonna be 9,8. We're saying A is the same as G, which is 9,8 meters per second squared. This is equation number 1. So this can only be used if we don't have any displacement. So if there is no displacement that is involved, that is the equation to use. Then case scenario number 2, or the equation number 2, if we have Vf squared must be equal to Vi squared, initial velocity squared, plus the 2a delta y. It can be delta y since we're just focusing on the vertical projectile. The distance moved is in the y direction. So this is equation number 2, and we only use this if we don't have any time. Okay, if you're not using time, then this is the equation to use. And then lastly, we have change in y. Delta y is equal to Vi times delta t plus a half a delta t squared. But what we are saying is that the a is gonna be replaced with a g. In most cases, a is gonna be replaced with a g. Now, depending on the direction of motion, okay, because we need to take also consideration when doing that. So I usually prefer to take upward motion to be negative, okay, if it is upward, and then downward motion to be positive. So if we're focusing on downward, then this will be a plus, plus, and plus. Then if it's an upward motion, this can be minus, minus, and minus. That is my approach. It's also believed, we know it can also work, whereby someone can take the downward motion to be negative, okay, and then the upward to be positive. You just need to state your case. You'll always get the same answers in whatever calculations you're gonna do, for as long as you maintain the signs that you deciding to go with. Okay, so having looked at that, I believe we're good to start with the questions. Okay, I'm just gonna go through some questions. If time allows, I'll cover as much as I can. Okay, question number 1. We're being told that a cricket ball of mass 156 grams is dropped from point A on a tall building that is 15 meters high, and then it strikes the concrete pavement, and then it bounces off. And then it bounces off. So this object is dropped, it falls, hits the floor, and then bounces off to a height of 4, maximum height of 4. Then they're asking us to calculate the velocity with which the cricket ball strikes the pavement. So for as long as an object is dropped, then the initial velocity is going to be 0. And this question is asking for the final velocity. So we're gonna say our initial velocity is 0, our final velocity is what we don't know, or what we're looking for. The only thing we've been given is the displacement, change in y, is being dropped from a height of 15 meters. Then we need to select which equation are we going to use. Since our focus is v final, we have the v initial and we have the displacement. So the equation to use would be the vf squared is equal to vi squared. Since the object is being dropped, we said I'm going to take positive to be the downward motion. This is 2g delta y. Then I'll do my substitution. So that's going to be our vi, which is 0 squared plus 2 times 9,8 times the displacement, which is 15. Okay, when I put that into my calculator, I'm just getting something like this is 2 times 9,8, is that true? And then times 15. So that gives me 294. So vf squared is 294, and then I need to find the square root. Okay, then the square root of my answer gives me 17,15 meters per second. Okay, that is question number 1. Then question number 2, 1.2. If the effects of air friction are not ignored, in other words, if they are put into consideration during the fall of the cricket, how would the value that you calculated here change? Will it be higher, will it be lower, or will it stay the same? So guys, what do you think? If there is resistance involved, if there is friction involved, what effects does friction have in the final velocity? So in this case, I'm gonna go for lower. Why? Because friction, we said, is a force that opposes motion. So for as long as it's trying to oppose motion, because the ball is falling downwards, friction will be acting upwards. So which means this ball is gonna fall with a lower velocity. Okay, and then 1.3, they're telling us that the cricket ball is in contact with the concrete for about 0.8 seconds. So that 0,8 is more of a reaction time. Okay, so if we ignore the effects of air friction and we are taking downward motion as positive, okay, calculate the impulse. What do we do when we are getting impulse? We know that from your momentum, impulse and stuff, you might have said that our F net is the same as change in momentum, the rate of change in momentum, something like that, delta P over delta T. Does that make some sense? F net is this. So when we talk of impulse, it's the change in momentum that we're focusing on, which means our change in momentum will be the F net times the delta T. But what is our F net? We know that F net can also be written as ma, m times the acceleration. And acceleration can also be expressed, since in this case we don't have the acceleration of the object, we can use the velocities, okay, and say the mass, which is v final minus v initial divided by the time. Mass times acceleration, which is v final minus v initial over t. We can use that as well before we can get to the actual answering of the question. Okay, so I'm just gonna erase this and just start over. Okay, so what I need to first of all find, what is the initial velocity or the final velocity that we're focusing on. So for as long as the cricket ball is in contact with the pavement for this much, and we're taking downward, calculate the impulse of the cricket ball on the pavement. So our final velocity is going to be assumed to be a 0. Okay, as soon as this ball strikes the ground, and then takes some time. Okay, initial velocity, I don't know that. My g is gonna be 9,8, and then I'm going to look at what's this. I'm gonna look at my displacement to be, is it 4? Yes, I'll look at my displacement to be 4. It makes sense though. Yeah, displacement is gonna be 4. And then from Vf is equal to Vf squared is equal to Vi squared plus 2g delta y. When I try to do the substitution with the 0, this is Vi squared plus 2 times 9,8 times 4. So now as I'm finding the velocity with which the ball started to rise up. Okay, so we are saying the ball strikes. It takes some time just on the pavement, and then it goes up to a height of 4. Okay, so the velocity with which the ball left the ground or the pavement is what I'm looking for. So when I do the maths here, this is gonna be, why am I taking 4? Why am I taking 4? Because it's moving upwards now. So it's gonna be negative 4. Okay, so that is 2 times 9,8 times 4, which is 78,4. So 78,4 is equal to the Vi squared, and then I find the square root of that, which is 8,85 meters per second. So this is just the initial velocity with which the ball is gonna leave the pavement. Then I will apply my F-net and delta P. Okay. So we know that our F-net times delta P is equal to the change in momentum. And we said this change in momentum is the same as AM V final minus V initial. When we do the substitution, what was the mass of the ball? They mentioned something like 156 grams. Change that to kilograms, it will be 0,156. What is our final velocity? It's negative 8,85. Since it's moving upwards, we are subtracting the initial, which was our final when the ball was striking the ground, which is 17,15 since it was taking the positive sort of direction. Okay, when I work this out, I'm just gonna get something like negative 4,056. This is mass, which is kilograms per meter squared. So since we're focusing on impulse, it's gonna be 4,056, but in which direction? It's gonna be upwards. Okay, then 1.3.2, they want us to get the net average force that is exerted. Okay, so since we know that our F net is delta P over delta T, our change in momentum is the negative 4,056, and we're dividing it by the time. The reaction time was 0,8 seconds from the information that we were given. So we divide it by 0,8. If that happens, then we're going to get negative 5,07 newtons. So this can also be written as 5,07, but upwards. Okay, so the force is going to act upwards. And then 1.4, they want us to sketch a position time graph. Now guys, we have different types of graphs when it comes to projectile motion. We have what we call the position time graph, we have the velocity time graph, and we also have what we call the acceleration versus time. Now we need to know how all of these look like. Okay, so if it's a position, in most cases it will take form of a curve, and then if it's a velocity time graph, we normally use straight lines to draw that. Okay, no, it's fine, we shall probably look at the different scenarios. So sketch the position versus time of motion which can go from the moment it is dropped up until it reaches the maximum height after the bouncing. So what we need to remember, they said position time graph. So on our y-axis, we're going to have our positions, and then on the x, we're going to have our time. So this is position, which position can also be represented as the y. Okay, and the question is, at what height did the object start falling? Okay, this position is in meters, this time is in seconds. So the object started falling from a height of 15. Okay, and then the object dropped. We don't know the time it took, we don't even need it at the moment. Then this object took some time on the ground, on the pavement, and then it rose again for a certain height. Which height we said was 4. So for as long as we have this, then we're good to go. So position time graph will always be a curve or be made of curves. So this is the reaction time. Okay, then 1.5. The cricket ball is now replaced with a softer ball, okay, of similar mass. They want us to state how the net average force exerted by the concrete pavement on the softer ball. With your answer, it's meant to be 1.3.2. We need to write only greater, smaller, or stays the same. So one thing we need to know is that from F net being delta P over delta T, change in momentum, we know that this net force is inversely proportional to the time. So if we are dealing with a soft ball is going to take more time on the pavement floor. In other words, the reaction time is going to increase. Okay, so when the reaction time increases, the net force decreases. Okay, so we're going to say delta T increases, which decreases the F net. So in other words, state how the exerted force is going to say smaller than. Okay, so the answer will be smaller than, because delta T increases, which decreases F net, because we know that delta T is inversely proportional to 1 over delta T. Okay, guys, that is question number 1. Then question number 2, it's more or less the same thing. We've been given a position time graph of a tennis ball. Okay, how do we approach a question when a graph is being provided for us? So they're telling us that the position time graph of a tennis ball that was thrown vertically upwards from a second floor of a school building shown below. Ignore the effects of friction. Okay, the height of the second floor is 6.5 meters. The ball rises 0.9 meters from the height of projection. Okay, so from here up to this point, that is 0.9 meters extra. Okay, before it starts to fall to the ground, so which means maximum height, an extra 0.9 meters. Okay, write down the magnitude and direction of acceleration of the ball while it's moving upwards. So the acceleration of the ball will always be 9.8 for as long as it's under projection or projectile motion. Okay, and this acceleration acts downwards. Regardless of whether it's projected up or down, it must always act downwards, since that is the initial direction of gravity. Okay, and then they want us to calculate T1, the time it takes the ball to reach the maximum height. Okay, one thing we know about maximum height is that the final velocity has to be a 0. That's one thing we need to know. Final velocity has to be a 0. So now, since we've been given displacements, we've been given the g's known to us, but we're focusing on the displacements. Let's say the distance traveled, Vy, is 0.9 meters. What else do we know? We know that our V initial, is it going to be a 0? It was projected vertically upwards from the second floor. Okay, so I'm not going to assume that. So I'm going to use this equation, Vf squared is equal to Vi squared plus 2 t delta y, something like this. So we are saying at the maximum height, final velocity is 0. Is that true? Yes. But the question is asking for the time it takes. Let me see if I can get an equation that has time straight away, so that I don't have to waste a lot of time. This is vi delta t plus a half delta t squared. And then f is vi plus a delta t. I have that. Do I have the initial velocity? No, I have the initial position. It's not gonna make sense. So which means I need to first of all get the initial velocity. Okay, so my vf is 0, my v squared I plus 2. Now the g is going to be negative 9,8 because the object is being projected upwards. And upward projection, I normally take g to be my negative. Okay, and then times the distance that the object traveled, which is the 0,9. Okay, when I sort that out, when I multiply that, I'm just going to use this to be positive since I've already considered the g to be negative. Okay, that is 2 times 9,8 times 0.9. That gives me 17,64. When I transpose that, vi squared is equal to 17,64. Find the square root. The square root of the answer is 4,2 meters per second. So this is the initial velocity. So having obtained the initial velocity, then I can use this equation here, the first equation of motion, and say my final velocity is 0. My initial is 4,2 plus it's gonna be negative 9,8 t. I hope that makes sense. When I move, if I transpose, I have 9,8 t is 4,2. Divide by 9,8 over 9,8. Okay, so 4,2 divided by 9,8, I'm getting 0,428 seconds, which will be more or less like 0,43 seconds. Okay. That is 0,43 seconds. So that is that. That is being it in 2 steps. But someone can even use this second equation, this, since you're looking for t, and then you get that straight away. Okay, and then 2.3, they want us to calculate the initial velocity of the tennis ball at the instant that it's released. At the instant that it's, so we've already calculated that, okay, which means we've used a very long approach, which has already even answered the next question, but it's fine. So we say this is a 0, vi squared plus 2 times the 9,8 negative times the 0,9. Okay, and what did we say? We just transposed that. So vi squared is 17,64. Then when we took square roots, our vi became 4,2 meters per second. There's no harm doing that again, as long as it's going to give us the max that we desire. Remember, all questions normally have different approaches, quite a number of approaches. Then 2.4. Now they want us to sketch a velocity time graph. Okay, they gave us a position time graph, they want us to sketch a velocity. So we said velocity is always made up of straight lines, no curves. Okay, then I can put my time somewhere here, which is in seconds. So if this is the origin, what was the initial velocity? The initial velocity was 4,2, the one we've just calculated in the previous question. And then it took some time, which was 0,42 seconds, so 43 seconds to get there, which we can label as our T1. And then the graph continues. So it's just a straight line from here into that sort of direction. We don't need to mark this off as 0,43. You can if you have time, no problem. So it's calling this point A, where the ball started from, and then point B, which is more like the maximum height. At the maximum height, that can be point B, and so on and so forth. So after the maximum point, this section just tells us the direction or the velocity of the ball when it's falling down. So that is what one would do. Someone say, all of this for 4 marks? Yes. For as long as you have a straight line, not a curve, you get a mark. Then for as long as this part is shorter than the other part, because remember, this A to B is just the section from point of release up to the maximum point, which was quite a small distance. Okay, and then the 4,2, for as long as you've indicated it, you'll also get a mark. And then the time T1, which is the 4,3, you get the last mark. Okay, then let's look at question number. We need to do this because I feel like it looks more or less the same as what we've done, but it's fine, not a problem. We can look at it. Then question number 3, they're telling us that the sketch below shows the motion of a ball that is thrown vertically upwards from a balcony, and it takes 0,4 seconds. Okay, to reach the highest point, after which it falls down past the balcony, boom, up to that. Then from the graph, how high is the balcony from the ground? So the ball is projected from the balcony, which means the distance from here up to there. That's how high the balcony is. So it's just 8 meters. And then 3.2, without any calculation, what is the numerical value of T1? T1, somebody? Remember, this is more like a parabola. And this 0,4, where the time is at the maximum, or the velocity is 0. That is the maximum height. This is acting as our axis of symmetry. So if this is 0,4, even this must be 0,4. So which means that is 0,8 seconds without any calculations. So that is just the logic. And then 3.3, they want the initial velocity. So we shall use more or less this, can use the first equation and say V final is equal to Vi plus A delta T, the initial velocity. So we can use the final velocity at this point of the maximum. Okay, so I'm gonna take the V final to be 0. Vi is what I need. I'm gonna say plus, I'm gonna use negative 9,8 times my delta T 0,4. Okay, so 9,8 times 0,4, I'm getting 3,92. Okay, then vi minus 3,92 is equal to 0. Then move it that side, which means the initial velocity is 3,92 meters per second. Which direction? It is basically upwards. It's upwards. Okay, and then 3.4, they want the maximum height above the ground that is reached by the ball. Now, since they're asking for maximum height, that is like displacement. Which displacement formula can we use? We can use. I don't know. Let's use the second equation, which is delta y is equal to vi times delta t plus a half a and then delta t squared. I think this can work. So they want the maximum height above the ground, so we're looking for delta y. So what is our initial velocity? We got it as 3,9. So guys, regardless of what value you get, for as long as that value is gonna be used in the next question, please use it, even if it's wrong. Okay, it will do you some good for consistency's sake. So the time was 0,4 seconds plus a half, since the direction of projection was upwards, gonna be negative 9,8, and then we're saying we're multiplying that by 0,4 squared. And I use my machine, 3,92 times 0,4 plus a half times negative 9,8 times 0,4 squared. I'm getting 0,78 meters. So this is just from the point of projection. So 0,78. So just from here up to there, that is 0,784. Now, since they're talking about from the ground, the distance from the ground, or the height from the ground, it's going to be the 8 plus the 0,784, which becomes 8,784 meters. And then lastly, no, it's not lastly, 0.5, calculate the magnitude of the final velocity of the ball when it reaches the ground. Okay, so in this case, we can look at number 1, either break down the journey into 2. Someone may choose to focus on the second part of the journey of the ball, which is like from the maximum point up here. Since we know that at this point, the velocity is 0, so which means this will be our initial velocity, and we're looking for the final velocity, which will be 0. This one, the initial velocity. The time it took, we don't know, but we can get an appropriate formula. Or alternatively, someone can take the entire journey of this ball and then still get to the same result. So in this case, I'm just gonna look at just from the maximum height, the first scenario. So if I use Vf squared is equal to Vi squared plus 2a delta y. Since I know my maximum height, I can use that. So they want the final velocity, so this is Vf squared. Initially, at the maximum height, the velocity was 0. So that's gonna be 0. Plus 2, our acceleration is negative 9,8. And then our height is 8,784. You could round that off to 2 decimals, there's no problem. So that is 2 times negative 9.8 times the 8.784. I'm getting, does that even make sense? Yes. I'm getting negative, no. If I use negative, then that means I'm using the initial root. But if I'm focusing on just the section from the maximum to, then this is meant to be positive. So that is 172,1664. That is Vf squared. And then I can find the square root of that. Square root, my answer, I'm getting 13,12. Okay, that's 13,120 meters. So that is going to be our maximum velocity or terminal velocity. So we said alternatively, someone can use that other route of the entire journey. Okay, so if you're using the route of the entire journey, then your displacement is just gonna be 8, because from the point of projection up to the same point of projection, the displacement is gonna be 0, and then we focus on just the 8. Okay, if we try that out, we said our initial velocity. Now let's try it out and see. Maybe let me just jot it down here. Just for the sake of space, I'll erase it. Okay, I'm using just the same thing. Vi squared plus 2a delta y. So we got our initial velocity as 3,92. That's what I want to use. So 3,92 squared plus 2 times now negative 9,8 times 8. 3,92 squared. Is this gonna make sense though? Something is fishy, something is fishy, something is fishy here. Guys, no, it's okay. Let's just ignore that and just use that formula. There's no need for second option. How does it test that? It's okay. Then 3.6, they want us to draw a velocity time graph. Okay, so if this is the velocity, and then that is the time in seconds, velocity in meters per second of the motion of the ball, indicate the following: initial velocity, final, and the time taken to reach the maximum. So our initial velocity, we said, was 3,92. Okay, and then the final velocity, we said it's 13. We said at maximum, what is the time? We said that was 0,4. So we're just gonna draw a line. It must be longer. And then we can put the 13 down. Then we can call this 13,12, but in the negative. Okay, it's not a big deal for as long as you have the initial or you have these 3. It's a mark for each. Okay, then we move on to the next question. Question number 4. Question number 4. What do they want us to do? They are telling us that a boy kicks a ball, okay, vertically upwards from a height of 0,6 meters above the ground. Then the ball moves past the top of the building 21 meters higher than the original point from where it was kicked. And then the ball hits the roof in 3,1 seconds after it was kicked. Then the ball bounces off the roof and then it comes to rest. So the ball is kicked, it goes up past, reaches maximum, hits the roof, bounces off, and then it gets to rest. Okay, then they're asking us to write down the magnitude and the direction of the acceleration of the ball at point X. Where is point X? So point X is not indicated on the question, but regardless of where that point is, even if it's there, even if wherever it is, I don't know whether it's that. So that's gonna be just 9,8, and the direction must always be, we say, downwards, for as long as it's gravity, as long as it's free fall. sorry, it's 9,8. I'm sorry guys, it's 9,8 meters per second squared. So now what about the units? Then 4.2, calculate the magnitude of velocity with which the ball was kicked. So we're looking for the initial velocity. What do we have in question? We know that this is 0,6 above, so which means the ball is going to travel 21 meters from where it was kicked. Okay, and it takes 3 comma where the ball hits the roof of the building, 3,1 seconds after it was. Okay, so I'm gonna look at the 21 from there up to there and then see. So if I look at my downward motion as positive, I can use delta y is equal to vi times delta t. Can use a half a delta t squared. Why? Because the question is asking for initial velocity, which is the vi. Only thing we have is the time and the displacement. Okay, so my displacement is gonna be the 21, which is negative. Initial velocity, I don't know. My time was 3,1, and then a half, my A is gonna be 9,8. Oh, why am I doing that? It's okay. And then the T is 3,1 squared. I'm using negative 21 because I'm taking the downward motion to be positive, which means my displacement when it moves up will be negative. I am not necessarily focusing on the G. Okay. When I do the substitution of all of this, I have a half times 9,8 times 3,1 squared. That's gonna give me 470. Okay. No, not 470, sorry. It's 9,8. It's 47. So the whole of this is giving me 47,089. And then I must move it that side. So say plus 21, which is like a 68,089. And then when I divide this by 3,1, I'm getting 21. So initial velocity is 21,96 meters per second, or any other acceptable option or equation can be used. And then calculate the maximum height that the ball reaches above the ground. Now, since the initial velocity that we're focusing on is 21,96 meters per second, they want us to get the maximum height, and we said at the maximum height the final velocity must be 0. We're looking for delta y. Okay, so we can use v squared, v final squared is equal to vi squared plus 2a delta y. Our v final, that is a 0, is equal to, I'm going to say 21,96 squared plus 2 times our a, which is 9,8. I'm going to call it negative because I'm taking gravity to be downwards. Okay, now I move it that side, it's going to be 19,6y. What is 21,96 squared? Getting 482,2416, then divide by 19,6, divide by 19,6. That cancels out. and then my y becomes 24.60 meters. So this is the maximum height that the boy is gonna reach. And then 4.4, being asked is referring to the sketch. Refer to the sketch and state whether the collision of the ball on the roof is elastic or inelastic. So since the ball reached the maximum height, it bounced off. Okay, so wait a moment. Is that question done? Calculate the maximum height that the ball reaches above the ground. Above the ground. We're not done. This 24 is, so remember, the ball was kicked from a height of 0.6. So which means we have to add the 0.6 also. Sorry. Plus the 0.6. Then that becomes 25.2 meters. Thank you. Then 4.4, we were saying the ball is gonna reach the maximum height and then it drops to the roof, just one bounce, and then it comes to rest. So is it elastic or inelastic? So I'm gonna say it's inelastic. The reason being, from the maximum height, the ball bounces, but the bounce just reaches a height that is lower than the maximum and then gets to rest. So we can say that the ball just does the bouncing. Ball bounces lower. Lower than the maximum height before. Lower than the maximum height that was reached. So had it been that the ball decided to bounce higher, then it was gonna be elastic. Okay, and then 4.5, they want us to sketch position. Remember I said position is a curve. Okay, position is measured in meters, and then time is measured in seconds. Okay, position time graph for the complete motion of the ball from the moment it was kicked until it comes to rest. Okay, so if I'm to look at it, remember the ball is gonna reach the maximum. We say 21. So if it is 21, okay, we have 21, and then which other height do we have? Okay, 4.2. Minus 24.6 minus 21, which is 3.6, which means the height of the bounce is 3.6. So in other words, it went up. This is gonna be like 21, and then there's an extra 3.6 for it to reach the maximum where the velocity is 0. So I'm gonna take this to be my 21 negative. Okay, and then to just move, it reaches a maximum height of how many meters? 3.6, because we say 24.6 minus the 21, which is 3.6. Okay, and then it bounces off. They told us the bounce takes place at a time of 3.1 seconds. Okay, and then it takes also another bounce Do we know that time for the next bounce? We don't know it, but it does before it comes to rest. So what we need is the initial starting point, the maximum point it reached, and then that other point. Okay guys, so that is question number 4. Question number 5. Question number 5, I think I'll have to stop at a question below what I'd prepared. So this is more or less still the same, but it's okay, we can look at it. They're telling us that Sandile, who is standing on a platform, throws a small metal ball vertically downwards, vertically up from the height of 1,73 above the ground. So this is 1,73 up. Okay. At this velocity, the ball travels past the top of the building and returns to the hand, who is still at that same height. Ignore the effects of friction. Sandile is somewhere here. So with what speed does the ball strike Sandile's hand? So the ball was projected at 8. So since Sandile is still just at the same point, we're gonna say it's 8 meters per second. Nothing changes. Since we are ignoring friction, it's just gravity that is doing the work. Okay, using the equation of motion and not energy principles, calculate the maximum height that the ball reaches above the ground. So Vf is gonna be 0. V initial, we have it as 8. A, which is G, is 9,8, and then the height is what we're looking for. So I'm gonna say Vf squared is equal to Vi squared plus 2 times acceleration delta y. Then we say that maximum height velocity must be 0. 0 squared, initially it's 8, and then since I'm projecting it upwards, it's gonna be negative 9,8 times the y. So 2 times 9,8, that's 19.6. So I'm gonna transpose it that side. So 19,6y is equal to 8 squared, which is a 64. Then I divide by 19,6. Okay, 64 divided by 19,6, I'm getting 3,27. 3,27 meters. That is from the point of projection. Okay, from here, or from wherever Sandile is, up to there. But now from the ground, since the question is talking about the ground, which means I'll have to add the 1,73 meters, which will make it, I don't know guys, help me, 1.73, which is 4,9995, which is, we'll round it off, it's just gonna be 5 meters above the ground. 5 meters above the ground, 5 meters above the ground. Okay. And then 5.3. So if a window on top of the building, on the top floor of the building is at 2,5 meters, calculate the time it's gonna take for the ball from the moment it was thrown to pass the top of the window on its return. So this is a quadratic, guys, a quadratic time it takes to pass the window. Okay, let's see. So we must be able to get at least two values if possible. So we can start by by doing what? We need to get the final velocity first of all, because in this case we're not focusing on the maximum height. We just want the velocity after the 2.5 meters of distance traveled by the ball. So that's going to be 8 squared plus 2 times 9.8 negative times the 2.5, because that is the distance from Sandile's hand to the window. Okay, when you sort this out, 8 squared plus 2 times negative 9.8 times 2.5 followed. What's going on? I'm getting 15 and square root of 15. So this is 15. And then square root of 15 is 3.873 meters per second. Okay, this is like our final velocity. And then if I use Vf is equal to Vi plus 80 or A delta T. Our V final, we have it 3.873. It's going to be negative. And then our initial velocity was 8. Our acceleration is negative 9.8 times a certain time. Okay, so when I move the 8 that side, it's gonna be minus 8, which is, I missed it, 3.873 plus 8, that's 11.873. Negative is equal to negative 9.8. Then I'll divide by 9.8 over 9.8. That cancels. What do we have? Getting 1.21 seconds. So they say every the time taken for the ball from the moment it was thrown to pass the top of the window on its return to Sandile's hands. So I'm getting 1.21 seconds. Okay, the reason as to why I'm using the 2.5 is because that top part is gonna cancel out to be 0 in terms of the displacement. Okay, since this part is gonna be the positive displacement and then this negative displacement is gonna cancel it out. That's why we're gonna just stay with the 2.5 meters. Then 5.4, taking upward direction as positive. Draw sketch of position. Time again. Guys, we said position is a curve. Taking upward as positive. Time is in seconds. Okay, so if we take our position in that sort of format, what do they want exactly? They want us to draw the ball's motion from the moment it left Sandile's hand until it lands back into his hands. Oops, okay. That is 0. That's pretty easy. Something like that. So what is the maximum height that, or the maximum position that we got? Somebody help us. It was 3.27. 3.27. So just indicate this. 3.27. Is there time that is needed? How long did it take? Do we know that? Is the window calculator time taken? And that is for the window. Nothing. So we can just leave it like that. So for as long as we have the correct 3.27, as long as the shape graph starts from 0, because that's our displacement, the ball was not moving at that point. As long as the shape is correct, and then we label this correctly with the correct units, then we're good to go. question number 6. I don't know, I feel like we should skip this, or I don't know. Skip it, do it. It's fine. Let's attempt it and see. So the ball is thrown vertically upwards at the velocity of 4 meters per second. 4 meters per second from the roof of a building with a height of 10 meters. And then the ball strikes the ground and rebounces to a height of 3 meters. Okay. Okay guys, let me work this out, but if the next question is more like the same, I'm gonna skip it, so that we look at just a different sort of scenario. Okay, so they want us to get the time taken for the ball to reach the maximum height. So we said maximum height, final velocity is 0. So our initial velocity is 4 meters per second. Okay, the ball strikes and rebounds to a height of 3 meters. So this is pretty quick. We can say Vf is Vi plus A delta T. Our V final is a 0. Our initial is 4. Since we're throwing the ball upwards, it's going to be negative 9,8 times T. Move the further side, which is 9,84. So 9,8 T is equal to 4. And then divide both sides by 9,8. 4 divided by 9,8. I'm going to get 0,41 seconds. If I round that off. And then they want us to get the maximum height that the ball reaches. So the maximum height, we need to get an equation that involves displacement. So I can use what just happened? Okay. So I'm saying I can use my delta y is equal to Vi delta T plus a half A delta T squared. I want the height. Do I have the time? Yes, the 0,4. Acceleration, I have it. So it's going to be 4 times 0,41 plus a half times negative 9,8 times 0,41 squared. I hope that makes sense. 0,4 plus 0,5 times negative 9,8 times 0,41 squared. I'm getting 0, is that true? Let me just redo it again. 4 times 0,41 plus a half times negative 9,8 times 0,41 squared. Okay, I'm getting 0,82 meters. Okay, so that is our maximum height. And then they are telling us that the ball strikes the ground 1,09 seconds after it was thrown and remains in contact for 0,2 before bouncing off. We need position versus time. Use the ground as a reference and indicate the following. So when they say indicate the following, this is what they're going to mark. Okay. So this is position in M. I'll say this is my time in seconds. So if that is a 0, at what point did the projection start? This ball was projected from 10 meters. So which means our story must start from a height of 10. Okay. So we're saying, I don't know, let me just throw something small. That's a 10. And then this ball is gonna move up to the maximum. What do we get as our maximum height, guys? It was 0,82. So 10 plus 0.82, that's gonna be 10.82. And then this moves. Okay. It hits rock bottom. You're telling us it spends some time. So at what time does it hit the ground? Strikes the ground at this. So this is 1.09. Okay. It stays on ground for 0.2. So 1.09 plus 0.2 is gonna be 1.29. Okay, and then it just bounces off to a height. Did they give us that height within the question? Yes, to a height of 3, which means this graph must stop at 3. So this must be at 3. It's just that. As long as you represent the height from which it was thrown, it's a mark. Maximum height reached is a mark. The height reached by the ball after bouncing the 3 meters, so it's a mark. And then the time it takes to strike the ground, it's a mark. Contact time, it's a mark, because the difference between that will be your 0.2 seconds. Okay guys, that is question number 6. Question 7. Okay, this is interesting. This is interesting. Telling us that ball A thrown vertically upwards from the top of the building, that is 8 meters high, at the velocity of this. At the same instant, there is another identical ball that is thrown upwards. So this goes down, and then this one goes up. Okay, it's thrown at the same kind of thing. So I'm gonna just summarize this and say ball A and then ball B. The height, initial velocity, say VI for both balls, telling us A is at 12. At the same instant, B is thrown upwards with a velocity of 30. A and B pass each other after time. So they will be equal to, or the distance traveled will be equal after this amount of time. Then give the direction and the acceleration of B while moving upwards. So one thing we said, they want the direction. We said direction of the acceleration. Acceleration will always act downwards. Okay. Then they want us to calculate the velocity of B, ball B, the moment it passes ball A. The velocity that A or B passes A. Okay, so I need to get the final velocity first of all. Final velocity that B is gonna be traveling with. So I'm gonna say V initial plus A times the delta T. Okay. So my initial was 12. Said calculate the velocity of B. Guys, I'm sorry now. We're looking at ball B, which is 30, not 12, plus the 9.8, which is gonna be negative. And then what distance is traveled? We said ball A and B pass each other after 2.13. So I'm gonna multiply that by 2.13 because I know they're gonna meet or they're gonna pass each other after 2.13 seconds. Then I'll do my substitution into the calculator. 3 plus negative 9.8 times 2.135, which is 9.077, which can be rounded off to 9.08 meters per second. Which direction? It's moving upwards. Okay. Then calculate the distance between A and B 2.5 seconds after it was projected. After it was projected. Okay. So I'm gonna use delta y is equal to vi delta t plus a half a delta t squared. Since they're asking us for distance, we know the vi, we know the t's. Okay, they gave us the t as 2.5. Acceleration, we know it. Okay, so I'm gonna look at probably both balls and see what's going on. There's ball A and then there's ball B. So if I focus on A, my displacement is gonna be our initial velocity was at 12, and the time that we're looking at is 2.5 seconds. And then plus, remember ball A was being thrown downwards, so the 9.8 is gonna be looked at as positive. And then times 2.5 squared. Okay, 12 times 2.5 plus 0.5 times 9.8 times 2.5 squared. That is giving me 60.625. 60.625 meters. So that is how far ball A would have traveled. And then when I look at ball B, okay, if I look at ball B, let me say what is 80 minus 60.625, which is 19, something. Oh, that makes sense. Calculate the distance between A and B. After this kind of time, let me just dissect this. So this would have traveled that much, which is 60.6 something. So what is left is 19.375. Okay, now I'll visit that again. Let me look at B. When I look at B and use the same kind of approach, it's gonna be my 30 times 2.5 plus a half times negative 9.8 times 2.5 squared. Okay, same 30 times 2.5 plus a half times negative 9.8 times 2.5 squared. That gives me 44.375 meters. So this is above the ground. That is above the ground. Okay, let me just do this. Okay, so I'm gonna look at B. So if B has traveled 44.375 from the ground, and we are saying A traveled as far as the 60, something and reached here, and what is left below the ground, we said it's 19.375. If I get my 80 minus the 60.625 to get what is left at the ground, so that for me to get what is shorting, I'll focus on the 19, something and this 44. I subtract the two to get the distance between. So 44.375 minus the 19.375, and then I get 25 meters. So it's just 25 meters between the two balls. Okay, then they want position time. Oh Lord, these people have position time. So this is position in meters, and then we're saying this is the time in seconds. Okay, so we have two balls, remember. One ball is starting from 0, another ball is starting from a certain height, which is 18. So this ball is gonna move in this sort of direction. Okay, I'm gonna use a different color for other balls. So which ball started from 0? It's ball B. I'll label this as a B. And then A started from somewhere there. And then it's gonna hit the ground. So we're saying at this point, when they pass each other, we were told that time is 2,135. 2,135 seconds. Okay. So for as long as we have this position in meters or displacement delta y in meters, time in seconds, and all of that, then we're good to go. Then question number 8. We've seen this, guys. We have seen this. I don't know. I'll beg to skip it. Should I, guys? Yes, I think I'm gonna skip it because it just looks the same. When you look at our first question, when you look at the second question also, it's just the same sort of approach. So I'm not gonna do that. Let me just go to question 9 and wind up. Okay, so we're saying question number 9. Ask is question 8. Next time. Okay, question 9. They're telling us there is a girl that stands on a platform in a classroom. She throws a ball vertically upwards to the floor, hoping that the ball, after it bounced on the ceiling, will hit the ceiling. What's going on? A girl stands on a platform in a classroom. She throws a ball vertically upwards to the floor. Okay, so this girl is standing somewhere here. Around source case, I don't know how to draw girls. Okay, she throws the ball to the ground, hoping that the ball, after it had bounced from the floor, it would hit the ceiling. Okay, then it's making sense. So she throws the ball with the speed of this. So our initial velocity is 8 meters per second, the height from above the floor. Okay, so that is the platform. Okay, we need to ignore the air friction, air resistance. Then they want us to write down the magnitude and direction of acceleration of the ball immediately after it left the hand. So acceleration, guys, it's a giveaway, this one. Direction, downwards. Acceleration, downwards, it's a must. The 9.2 is the motion of the ball while it's moving downwards towards the floor. Is it free fall? Yes or no? The answer is a yes. Since we are ignoring the effects of air friction, and this ball is just falling under the influence of gravity. So we are saying only gravity. It's only gravity that is acting on the ball. Only gravity acts on the ball. Or we can look at the influence of gravity on the ball, or the ball is moving under the influence of G. The 9.3, they want us to get the magnitude of the velocity with which the ball hits the ground. So magnitude with which the ball hits the ground, they want us to get the VF, final velocity. We said our initial was 8. Initial velocity was 8. G is 9,8. Do we have the time it takes? Anything? They only gave us the height. which means the displacement is, excuse guys, displacement is 1,8 meters. So we can use the VF squared. Yeah, VF squared is equal to VI squared plus 2A delta Y. We're looking for VF. Okay, so our VI is 8 squared plus 2. Since the ball is dropped down, so it's gonna be positive 9,8, and then the height is 1,8. So 8 squared plus 2 times 9,8 times 1,8. That gives me 9 to 9. So VF squared is 99,28. Then I must find the square root. So square root of my answer is 9,96. Okay, 96 meters per second. So that is the final velocity when the ball strikes the ground. Okay, then 9.4, how long does it take the ball to hit the floor? So we're looking for the delta t. Since we have our VF, we can even use that first equation. The VF is equal to VI plus the A delta t. I feel that is way quicker. It's VI plus A times delta t. So our VF, we said it's 9,96, is equal to the initial velocity, which we said was 8, plus our acceleration, which is 9,8 t. Positive since the ball is being dropped. Move the 8 that side. 9.96 minus 8 is going to be 1,96. 1,96 then divided by 9,8. So which means t is 2 seconds. Is it 2? Wait, 1,96 divided by 9,8 is 0,2. 0,2 seconds. Okay, and then the ball bounces inelastically on the floor. This simply means it's just gonna bounce off below the height of projection. So it bounces off inelastically on the floor where the speed of the ball decreases by 20%. And then the ball is in contact with the floor for 0,01 seconds. And they want us to determine by means of calculation whether the ball will reach the ceiling after it bounced off. So inelastically simply means the height kind of decreased compared to what was expected. Now, since they gave us 20%, they are telling us that it decreases by 20%. So someone can find 20 of the final velocity, which we got as 9,96, and then you subtract 9,96 minus this 20 over that. So it's 9,96 minus 0,2 times 9,96. I'm getting 7,97. Okay, that is 7,97. So this is gonna be the new velocity. Okay, they want us to determine whether it will reach the ceiling. Remember, our ceiling is at which height? 3,5 meters. So we need to find the displacement and see if our displacement is going to be 3,5. Okay, so if we get VF squared is equal to VI squared plus 2 times A. Oh god, so I think I'm tired now. I said A delta Y. Okay, we're looking for the displacement. We have the acceleration, we have the initial, we have the final. Yes. So we're looking for the maximum height that the ball is going to reach. And the maximum height, we said velocity will be 0. So 0 is the same as 7,97 squared. Now someone will ask, why are we using this? Remember, as the ball hits the ground, it spends some time there. The velocity decreases, and then the velocity with which it leaves, the velocity with which it bounces off. So let's say there was no 0,01 seconds. Then the velocity with which it hits the ground would be more or less literally the velocity with which it leaves. So in as much as it was the final velocity for the first journey, it's going to be the initial velocity for the next journey of the bounce. Okay, 2 times 9,8 delta y, it's negative since it's moving up. Okay, when I simplify that, 7,97 squared, I'm getting 63,521 minus 19,6 y is equal to 0. Move it that side, 19,6 y, then divide both sides by 19,6. Okay, and then our y is going to be divide by 19,6. I'm getting 3,24 meters here. Okay, so since the maximum height I'm getting is 3,24, and they told us that the maximum height out to the ceiling is 3,5, which means this ball is not going to reach the ceiling. Okay, so determine by means of equation whether the ball will reach the ceiling. So the answer is nope, the ball ain't going to reach the ceiling. The ball won't reach the ceiling. Will not reach the ceiling with the target point. Alright, that is 9.5. And then 9.6, lastly, they want us to sketch a velocity time graph. Our first colleagues, this is velocity in meters per second. And then we're saying this is time measured in seconds. So if we look at velocity, remember we said velocity time graphs are basically straight lines. Now at what velocity did the journey start? So it started with 8 because that was the initial velocity. We worked out our final and we got 9,96. Yes, 9697. It's 96. Use a different color. Okay, so this is 9,96. Sorry if my rounding off was poor. And then at what time was that? After how many seconds? It was 0,2 seconds. It was 0,2 seconds. We found it. Let's see. Okay. And then from this point, what happens next? There is a 9,97 when it is doing the bouncing off. So I'm gonna put it 9,97. So which means this is also 7. Okay, when it is bouncing off, so I'm just gonna have this line to that point, and then I'm gonna have, they said it takes 0,01. So this is gonna be 0,21 seconds. So which means my line must pass the middle point, and this must correspond to this 9, something, and then it reaches 0, since it's gonna reach the maximum point of the 3,24. So straight line, then straight line. Okay, and then lastly, question number 10. Telling us a boy throws a ball vertically into the air from the top of a building, and then the ball strikes the ground after 4,08. The velocity time graph has been drawn for the entire motion. Ignore the effects of friction. Okay, there is our definition question. What is a projectile? You said projectile was any body that was under the influence of acceleration with gravity. So a body, or we can say an object. An object that is acted upon by only acceleration due to gravity. Acceleration due to gravity. That's the only force. I'm sorry guys, my English, my repetition things. So an object that is acted upon by acceleration due to gravity, strictly acceleration due to gravity, is a projectile. Then what is the acceleration of the ball at 1,02 seconds? Remember, this is a velocity time graph. Okay, and for us to get acceleration is change in velocity over the change in time. You can use those formulas, equations of motion, but there is no need for that. Okay, so if you look at the change in velocity over the change in times, is 9,8 divided by 1,02, getting 9,61 downwards. Okay, that is if I'm to use the graph. Okay, acceleration of the ball at this time. So it's a two-way thing. Since we said an object acted upon by only acceleration due to gravity is a projectile, and this thing is just showing us the velocity time graph, and then they ask us for the acceleration, which means someone can say it's 9,8 meters per second squared downwards. But if we are to use the figures on the graph, change in velocity is going to be 9,8 over the 1,02. How are we getting the 9,8? Remember, we're getting the change, the gradient, change in V over the change in T. So that is what is giving me the 9,6. So it's fine, whichever option you go for, it's correct. So this 9,6 is taking into impact or into effect the values or the effects of frictional force. That's why it is even smaller. And then 10.3, they want us to get the displacement of the ball. So with the displacement, they want the delta y. Okay, we know that delta t is 4,08. Okay, so I'll say delta y is the same as vi delta t plus a half a delta t squared. Our initial velocity was it 0? No, it was 9,8. The starting velocity was 9,8. So that's 9,8, and then the time that we're focusing on is 4,08 plus a half. What is happening to the object is thrown into from the top. So I'm gonna take it to be negative. And then the time is still 4,08 squared. So when I punch that into the calculator, 9,8 on that, I'm getting 41,58 negative. So which means the displacement is downwards, 41,58 meters downwards. Then they want you to sketch the position time, and those are the things to look out for. So I'll say y in meters, and then this is the time in seconds. So number one, where did the graph start from, or where did the object? So that is the 0. And what time did it reach 0? What time was the velocity 0? It's after 1,02. So 1,02. The displacement was 0, or the velocity was 0, so that's the maximum displacement. And since it's more like a parabola, twice that is going to be 2,04. Means the graph must also pass through that point. Then we need the time of 4,08, which is twice that. So it's gonna be, so this is the maximum height. And displacement is 0 at that time. And this graph continues. Yo guys, I'm horrible at drawing. Let's do this. Okay, thank you. Something like that. So this position here, this displacement is what we just calculated in the previous question at a time of 4,08. Our displacement was 41,5 something. 41,58. 41,58. Okay. So 41,58 meters. So guys, for as long as you just show us the t values and the direction and everything, then we shall be good to go. And then other thing is about someone asked now, how about the acceleration time graph? How do they look like? So acceleration is not that hard. I'll just give you, guys, move. Erasing is not working. Okay, so if we have an acceleration time graph, it's just let's see. Okay. So that will be acceleration, and then this will be the time. So it's usually just straight lines. So this is an acceleration time graph, depending on which acceleration you're taking to be positive. So this will be 9,8. So it's just uniform, since it never changes. Sometimes it can be drawn like this, and then like that, depending on how the object is moving. Okay, Guys, I think that's enough for the day. What we haven't looked at, probably in the next episode. Let's meet. Hello and welcome to this episode of Physics. Before we go into details, we need to know that electrostatics is just a branch of science. Okay? Branch of science that deals with the study. Of charges or charged particles. Okay? So from this branch of science, we know that like charges that are having the same charges that are the same, so positive and positive or negative and negative, those charges will repel, and then the unlike charges will attract each other. Okay, like charges will attract each other. So this we need to know. Now, what if we have charges that are at rest? Okay, so if we have charges at rest, then there is a force that will be acting between those two charges. It can either be a force of attraction or a force of repulsion. So for charges at rest, we know that the force between them is what we call the electrostatic force. The electrostatic force. So what does this force do between the charges? So one thing we need to know and remember is that there's a German scientist known by the names of Coulomb that did a thorough study. What really happens when two charges are at rest and what sort of force works between them and what the relationship of force is, the charges and the distance between the charges themselves. So upon his conclusion, he said that this force is directly proportional to the magnitude of the charges, the Q1 times product of magnitude of the charges, not forces, and then it is inversely proportional to the square of the distance of separation. So it's just more like related with the universal law of gravitation for Newton, whereby you look at the force being directly proportional to the masses and inversely proportional to the distance of separation. But in this case, we're focusing on the charges. So if the proportionality symbol was to be eliminated, then K will have to be introduced, whereby F is representing the force, that is the distance of separation. These are the charges, and then K is what we call electrostatic constant. Okay, the constant of electrostatics, which is the same as 9 times the positive 9. Constant that we need to remember. So for any given two charges at a time, this formula will be used. So this formula brings about what we call Coulomb's law. Coulomb's law of electrostatics. Okay, so what does that law state? We are saying that the magnitude of the electrostatic force is the magnitude of the electrostatic force. Magnitude of the electrostatic force in between 2-point charges. Between 2-point charges is directly proportional. Directly proportional. The product, okay, the charges, or magnitude of the charges, and inversely proportional. Inversely proportional, the square of the distance between them. So the square of the distance between the charges. Sometimes we even talk about the centers. Okay, so that is what the formula says. Force is directly proportional to Q1 times Q2 over R squared. So that is Coulomb's law. We just need to know how we state that. So it's saying it's just similar to the universal where there is a G, and in this case we just have K. Now, what if we have, let's say, we have an example. We have this as our sphere number 1, I'll call it A. And then this is sphere number 2, I'll name it as a B. And then let's say we have distance from the centers, I'll just say 15 millimeters. Okay? Just for convenience, what if I use this as a 6 MC? And then I can use this as a 12 micro with a C. Okay? And then I need to get the force, the electrostatic force between the two. So both of them are positives, it's fine. I have no problem with that. So we know that our Q1, let me call this Q1, and then let me label this as the Q2. So if that's the case, so this N usually represents what we call nano. And nano is times 10 to the negative 9. So the overall charge is going to be 6 times 10 to the negative 9. And then this symbol mu represents micro in electrostatics times 10 to the negative 6. So the charge here is 12 times 10 to the negative 6 coulombs. This distance needs to be converted to the standard unit in meters. So my force, if I use that formula, is going to be K, which is 9 times 10 to the 9. And then I'm multiplying by 6 times 10 to the negative 9. And then I'm multiplying by 12 times 10 to the negative 6. And then I'm dividing it by the distance. We said it was 15 millimeters. When you're changing or converting millimeters to meters, you usually divide by 1,000. Okay, so you can do that, or you can multiply by 10 to the negative 3, whichever one is easier. That's going to be 0,015. Then I'll square that. Okay, so when I put that into the calculator, times 2 to the negative 6, and then I'm dividing by 0,015 squared. That becomes just 4,13 joules. Okay, so that is the force that is existing between the two. Now, one thing we need to know is that that force is what A is having on B, and then it's the same force that B is having on A. In other words, it's more like Newton's law, Newton number 3. As in opposite and reaction will be equal, but opposite. So the force that A impacts on A impacts on B is the same as that B impacts on A in the opposite direction. So since the charges are the same, which means it's going to be repulsion that takes place. Okay, that is just a simple scenario. Now, what if we have, let's say, 3 bodies? Okay, something like this. And then maybe we're given a distance of 12, maybe you're given a distance of 16 with different charges. I call this A, B, and then C. Let me call this 8 microcoulombs. I'll call this 9 microcoulombs. And then maybe 16 microcoulombs. For this centimeter, no problem. Now, if it is 3 charges, what we normally look at is you might be asked for the net electrostatic force. Okay, net electrostatic force of, let's say, A. Net electrostatic force on A as a result of B and then C. The net electrostatic force on A as a result of B and then C. Or we can say the net electrostatic force on B as a result of A and C. So in most cases, it's all about combining the two charges. Let me see how we can do this very fast. Okay? So since I'm looking for the net electrostatic force on A due to B and C, step number 1, I need to get the force between A and B. Okay? So force A and B, remember we said QA times QB over the RAB squared. So when I do my substitution, that is 9 times 10 to the 9, and then times 8, we said micro is 10 to the negative 6. And then this is 9 times 10 to the negative 6. Distance of separation is 12 centimeters, which will be 0.12 squared. And I convert that to meters. So that's a 9 times 8 times 9 times 10. I'm gonna put that negative, okay. And then we're saying this is 0.12 squared. Okay, so this gives me just 45 Newton. Okay. Now that is the force on A as a result of B. So since the charges are opposite, then there's going to be attraction. So it's moving to the left. Okay, then I need to find also the force between A and C. The force between A and C. So the formula, that is QA QC over RAC squared. So 9 times 10 to the 9, that is 10 to the negative 6. Then 10 times 10, that's gonna be to the negative 6. Now the distance we have in 12 and then 16. Okay, so 12 plus 16, that is 28. That's 0.28, but squared. When I put that into my machine, 9 times 8 times 60, okay, then I'm dividing by 0.28 squared. I'm having 16.53. Yeah, Newton. Now, since the charges are the same, this is a positive and then this is also a positive, there's going to be repulsion. So that force is going to act to the right. Okay, so that is the right. Now, for me to get the net, I must get the F of AB plus the F of AC. I do the substitution. So if my left is a negative, then I'm going to have negative of 45 Newton plus 16.5. So negative of 45 plus 16.53, ending up with 28.47 Newtons to the left. Okay, so that will be the net electrostatic force if, let's say, I have direct point charges. Then what if the point charges are just at an angle? Okay, an angle of, let's say, 90 degrees. Okay, let's say I have A here. Let's say I have another charge B, and then I have another charge that is C. Let's call the distance here, I don't know, let me call it a 2 meter. I'll call this a 3 meter, just to make it drop it easy. So I'm gonna call this negative 3 nanocoulomb. I'll call this a positive 4 nanocoulomb, and then I'll call this positive 6 nanocoulomb. Okay. Now, if this is the case, and then they ask us determine the net electrostatic force. Okay, net electrostatic force on B due to A and C. Okay, the net force on B as a result of A and C. Now, this represents what we call the 2D kind of electrostatics, whereby we have the horizontal as well as the vertical dimensions involved. So what we need to find the force that is acting within the vertical as well as the force that is within the horizontal. So this is F vertical, and then this is going to be F horizontal. So the net force for both needs to be found. So I'm going to get the force vertical. Remember we said AQA, QB over R squared. Force on B as a result of A. So if our A was a negative 3, that is 10 to the 9 times, we're saying 3 times 10 to the negative 9 because of the A. And then we are multiplying by 4 times 10 to the negative 9. Distance of separation is 2. I'll just square that. Okay. When I punch that into my calculator, having 9 times 3 times 4. Okay. Over that. This means 7 times 10 to the negative 9. That is newtons. But since the charges are opposite, there's going to be repulsion. So this is going to act downwards. And then let's look at the force horizontal. With the horizontal force, I'll be looking at QB times QC over R squared. 9 times 10 to the 9 times 4 times 10 to the negative 9 times 6 times 10 to the negative 9. I'm dividing it by 2 squared. Okay, so this is going to give me 24 times 10 to the negative 9. Now, since the charges are the same, it's going to be repulsion. So that is to the right. Is it to the left or to the right? Does it matter? It does. To the left and to the right. So that's going to be, remember, let's go back. Let's just go back a bit. Remember, there's going to be attraction. Force is up, is acting downwards. So this is going to be up. Okay? And then this is going to be to the left. This force is inverse. Just focusing on B alone. Okay. Then if we look at the forces, so it's going to be something like this. force vertical and then the force horizontal. So this is a 27 times 10 to the negative 9. We're saying this is 24 times 10 to the negative 9. We need to find our resultant. Okay. For us to find the resultant, we use the theorem of Pythagoras. R squared is equal to x squared plus y squared. F horizontal squared plus F vertical squared is equal to our F resultant squared. So 27 times 10 to the negative 9 squared plus 24 times 10 to the negative 9 but squared. So I'm going to find square root so that I have my F resultant. Okay, I need brackets here. Is 10 to the negative 9. And then I'll square it. We're saying plus 24 brackets is times 10 to the negative 9. But also squared. Okay, I'm having a very small number. It is 1, 2, 3, 4, 5, 6, 7. So 3,612 times 10 to the negative 8 meters. So that is the net electrostatic. Now we also need to find the direction. So with the direction, you need to use the fig where we look at the angle of inclination, which is the arctan of the F vertical over the F horizontal. Okay, shift tan. Our vertical was 27 times 10 to the negative 9 over 24 times 10 to the negative 9. If I put this into my machine, I'm going to have, what am I having? 8,37 or 37 degrees. So that will represent our angle, and then that is our magnitude. Alright, so that is if we are being asked to determine the electrostatic force or the net electric force. Then I just want us to look at what we call the electric field. Okay, so electric field is basically a region of space. A region of space where a charged body, sometimes it's a charged body, will experience force. At times we say it's a region of space in which an electric charge experiences a force. So the direction direction of the field at a point in space is the direction in which a positive one charge would move if it was placed. So direction that this force will be operating on that object is just the direction that a positive one charge would take if it was placed within that region of space. Then we also have what we have electric field point. Okay, maybe let us try that also. Electric field, the point where we say is the force per unit positive charge is placed at the point. The force per unit positive charge placed at that point. We shall go in details when we look at some examples. Then we also need to remember how to represent, let's say, the electric fields. An example, if you're looking at an isolated positively charged sphere. So we know that the field lines must be moved out of here. normally use arrows in that sort of manner. What if it's negatively charged? Then the field lines should be seen just entering into this. Okay. Now what if we have, let's say, two charged bodies? Remember we said positive and positive. That will be a repulsion. Okay. Now the technique with drawing this, the repulsion, we shall have, and then the field lines must not cross each other. Field lines must never cross path of each other. Must go in. So since they are positive, then the field lines seem just leaving. Same story here. Then the magnitude sometimes will also determine how many field lines leave the sphere or enter into the sphere. Sphere with a bigger magnitude will have more field lines. Those with smaller magnitude will see few field lines. And then if it's negative and negative, so still it's going to be repulsion. Yeah. You must touch the sphere. As long as we see the correct pattern and correct format of the field line. So the arrows should be seen entering into the sphere for as long as they are negatively charged. Now this region of space, there will be no force for, because the net force there is 0. So sometimes, let's say if you're talking about the electric field, sometimes you can put a positive Q here or a negative Q there, and then see what will happen. Then what if the charges are opposite? That's when we say it, we shall look at the attraction. A positively charged or negatively charged, we should be able to see field lines that are leaving positive spheres and moving into negatively charged sphere. Leaving something like that. Doesn't matter how it looks like, for as long as we see field lines leaving the positive and getting into the negatively charged. Now the formula for electric field. The formula for electric field, we know, must be given as E is equal to F over Q, where E is the electric field, and then F will be that force at that point, and then Q will be the charge, the magnetic charge. Now, if let's say we were to focus on the electrostatic force between the electrostatic force between, let's say, the big Q and then the small positive Q. From the Coulomb's law, we know that that would be K times Q, then times a small q over the distance of separation. So if we do the substitution, it's going to be K Q, that Q over R squared times Q. So this is going to cancel that out, and that leads us to this other formula which we normally use, is equal to KQ over R squared. So remember, the force due to the test charge. Then due to the test charge. So that we need to remember as well. Then if let's say we want that force, we can just cross multiply that so that we get the times the magnitude of that charge. Then one other thing that I can probably say is that whenever we have, let's say, the net electrostatic force or the net electric field being zero, simply means the charges must be opposite, or the electric field have to be opposite in direction. Okay, guys, that's a brief sort of start. Then let me just look at the examination guideline. So with the examination guideline, what is expected of us? Number one, we need to know how to state Coulomb's law, that the magnitude of electrostatic force exerted by one point charge on another is directly proportional to the magnitudes of the charges and inversely proportional to the distance in them. To be able to solve problems using this equation, this Coulomb's law, that is for 1D, where the charges are placed in a single line. And then solve problems with a 2D, where we have a 90-degree somewhere, somehow. And then we show, when we look at, let's say, the electric field, we need to be able to describe an electric field as a region of space in which an electric charge experiences force. The direction of the field at a point, the direction at a positive one charge. Okay, we need to be able to draw the field patterns for a single point charge. What if there are 2 point charges? What if they are charged spheres? Then we need to define electric field at a point being the electrostatic force experienced per unit positive charge placed at that point. We saw that. And then we should be able to use this formula, the E is equal to F over Q. Then solve problems with that formula. Then calculate the electric field at a point, the number of charges, and so on and so forth. Okay. So this is the examination guideline, and that is what exactly is expected of us. Then we need to look at some worked examples, so exam type questions. This is okay. Question number 1. I can start from question number 1. Next one. All right. So question number 1 is telling us if we have 2 spheres, M and N. 2 spheres, M and N, on insulated point M with a charge of -4 nanocoulomb that is placed 8 millimeters away from from A. Is a point that is K, and so on and so forth. Then they are telling us that the net, in capital letters, no? The net electric field strength is acting east. So we don't know the magnitude of N. We only have E. So the E net is 2 times 10 to the 5. This distance needs to be converted to meters. Okay. You know that that's -4 times 10 to the -9 coulombs. All right, let's see. So define the term electric field point. So we say this is the force that is experienced, okay, but per unit positive charge. Per unit positive charge placed at that point. Placed at point or placed at that point. Okay, that is if they ask you to define electric field at a point. That would be it. Then calculate the magnitude and direction of the electric field at P as a result of electric field at P as a result of electric field between P and M. So from our formula, we said E is equal to KQ over R squared. We know that K is 9 times 10 to the 9. Charge, we said it was -4, but we don't need the negative sign. Just magnitude, that's 4 times 10 to the -9. And then the distance of separation is 15 millimeters. Convert that to meters. So that's going to be 0,015 squared. Okay, when I put that into the machine, I'm getting 0.15 squared. I'm getting 1,000. Okay, 1,000 Newton per Coulomb. Now, which direction is it? So they want the electric field at P, the result of P. So since we're taking this to be a positive one, and then there's a negative, there's going to be attraction. Okay, so the force at P is moving to the east or to the right. To the right. Then they want us to get the magnitude of the charge on N. Magnitude of the charge on N. So since we have the net electric field, I think we can use electric field. Then we can find the electric field at P as a result of N, which will be K, the Q of N over R squared. So that at the end we have our E net being the E as a result of M plus the E as a result of N. Something like that. So since we have the first one, we just need to play around with that. So I'm going to say 9 times 10 to the next equals 9 times the charge of N over the distance between P and N, 15 and 45, 0,05 squared. Okay, when I put that into my machine, 0,045 squared, having a very big piece. Just 1, 2, 3, 4, 5, 6, 12. It's gonna make sense. It's gonna make sense for that's 12. I don't know. Let me just check it. I'm having 4,44 times 10 to the 12 QN. Okay. So the net that side was 2 times 10 to the 5. So the net is 2 times 10 to the 5. We are saying this is equal to the 1,000 plus 4,44 times 10 to the 12 QL. Yeah. Okay. Now someone asked, why are we adding them? Now, since the net force or the net electric field is acting eastwards, which means all of the charges, all the electric fields must be in the direction. So we are moving this one in the east. So then I'll move this to that side. So 2 times 10 to the 5. Then I will subtract my 160 tau. My 160 tau, I'm getting 40 tau. Is equal to 4.44 times 10 to the positive 12 Qn. Divide by 4.44 times 10 to the 12. Divide by 4.44 times 10 to the 12. This cancels that. Remember, we said we're going to subtract when you transpose that. So Qn going to be 4.44 times 10 12. Okay, I'm having 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm having 9,01. And it's going to the negative 9 coulombs. Or someone can say that is 9 nanocoulomb. Now with the charge, it will be positive. Nothing here. Then 1.4 is the charge on the sphere, positive or negative. Answer that. Positive. And then they want us to sketch the net electric field perpendicular to M and N. Now we said it's positive, and then the original, this one, was negative. So that is a positively charged and negatively charged attraction. Unlike charges attract each other. So, unlike charges must repel. Whereas the like charges, unlike charges must attract. Whereas the like charges do the repulsion. Then calculate the magnitude of the electric force that an electron will experience when placed. Calculate the magnitude of the electric force. Guys, how do we go about that? Okay. So we know that E is equal to F over Q. E is equal to F over Q. And what did we say? We say that so I'm still on the same question. Yes. Okay, calculate the magnitude of electric force an electron. Okay, since we're focusing on an electron, would experience when placed at that point. So since we have the electric field, the net electric field, we just need to multiply. So Q times E, we know the charge of an electron is going to be the one of times 10 to the negative, as I need the electron charge with my formula. Okay, so I'll get my net, which was 2 times 10 to the 5. And then I'm just going to multiply it by the charge of electrons, which is 1,6. And just confirm. So saying electron charge. Okay. So it's 1,6 times 10 to the negative 9. Okay, so when I multiply, it's true, you can put the negative sign, there's no problem. When I substitute that, 2 times 1.2, I'm having 3,2 times 10 to the negative 8. It will be newtons. Guys, that will be it with that first question. Then my question number 2. They're telling me that the diagram below shows two spheres A having that much charge and sphere B insulated. Distance between them is that. And they want us to draw the field pattern. So a negative and a positive. You know what to do. Attraction. Attraction. So we just so field lines should be seen leaving. Field lines should be seen entering. What's wrong with me? decentralized things. Say, say, like that. All right, then 2.2, calculate the magnitude and direction of the force exerted by B on sphere A. Okay, so from electrostatic force, we said F is A Q1 Q2 over R squared. That's 9 times 10 to the 9. The charge on A is 4,5. 10 to the negative 5. 4,5 times 10 to the negative 5. That is 9,5 times 10 to the negative 5. Distance of separation is 0,35. Okay, and then I'll square that. Putting this into the machine, I'm gonna have 9 times 10 to the 9. That's 4,5 for the multiplication. Okay, then we multiply by the 9,5 times 2, okay, that much, over 0,35 squared. Having 314,08. But since we're focusing on B on A, then the direction is going to be the right. B on A, the right. They give an attraction. Then calculate the strength of the electric field at B, the result of the strength at B. So we're gonna assume that instead of having the charge of B, just have a positive, because they're asking for the strength at B as a result of B. So that will be E is equal to KQ over R squared. 9 times 10 to the 9. And then we need the charge of A. So it was 4,5 times 10 to the negative 5 over the distance is still the same. Okay, so that's going to be 9 times 10 to the 9. Multiplying it by 4,5 times 10 to the negative 5 over 0,35 squared. Very short number. 3, 1, 2, 3, 4, 5. So I'll say 3,31 times 10 plus. Since the electric field is Newton per Coulomb, also going back to the right. Okay, question number 3. Two identical spheres again, A, B insulated and stands are placed with centers having 10 meters apart. Shown the sketch. So the charge on A is negative 10 nanocoulomb. And then B carries some charge that we don't know. Then the net electric field that. So this is more like this question. Find electric field at a point. Remember we said electric field at a point is the force per unit positive charge that is placed at a particular point. I'm not going to write that. Then they want us to draw the field pattern A and B due to charges A and B. Now, since the net force is acting to the left, but it will be at this point, acting to the left. What do you think? What do you suggest? What do you think? So simply means that since it's negative charge and the net force is the left, so it means force between this and it is also left. So it means it's more like and attraction force. Okay, that means I'm going to have a positive, then I have a negative. What that means? Attraction. Okay. That is attraction. And then they want us to get the magnitude of sphere B. So in that case, I'm going to use electric field. Okay, so I need to get the electric field between between A and P. And then the electric field between B and P. Then I use the net. Okay, so electric field of PA will be KQ over R squared. That's 9 times 10 to the 9. The Q we said was negative 10. Okay, I'm dividing by 2 centimeters, 0.04 squared. So put that into the machine. I'm having 9 times 10 over 0.02 squared. Having 337,500 Newton per Coulomb. Then I'm having the E to B, which is Q over R squared. That's 9 times 10 to the 9. That is the QB over 0.08 squared. Simplify that. Having 0.08 squared. Sure, very big number. Scale, I'll count 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. It's 1,4,1 times 10 to the 12. I'll call that cubic. Then now look at our inlet being the same as the ETA plus the ETB. Now the net that they gave us was 3,943. 3,943 times 10 to the 5 is equal to 337,500 plus the 1,41 times 10 to the 12, but QB. So I need to take this aside using subtraction. Okay. So when I do that, I have 3,945 times 10 to the 5 minus 337,500, which gives me 5,000. 1,41 10 to the 12 QB. Then divide both sides by 1,41 times 10 to the 12. That cancels that. Let's see 1,41 times 10 to the 12. Sorry for rounding off in advance, but it will make just little difference. So the charge on B, I'm having 1, 2, 3, 4, 5, 7, 8, 4,04 times 10 to the negative 8. Guys, that's that. Then they're telling us that sphere B is removed. State whether the electric field at P due to the charge A will increase or remain the same. So, since P is removed, it's having an effect on the net electric field at P. If it's removed, automatically it's going to decrease. Okay, then question number 4. Okay. They are telling us that 300 microcoulomb charges ABC qualifies expression meters on a straight line in a vacuum. Distances at razors and so on. Define electric field at a point. We say it's a region. Is this a region of space? No. Force by unit positive charge that is placed at that point. Point 1 answered. Then they want us to draw electric field lines associated with A only, since it's a positively charged sphere or object. Then the field lines should be seen moving out. So direction, so straight line, getting lines. 4.3, they want the magnitude of the electric field strength at position where B is and B to A only. So the electric field at this point B as a result of A. So if we place a positive 1 there, we shall ignore the charge of B. So that's going to be E being KQ over R squared. 9 times 10 to the 9, that's 100 times 10 to the negative. Distance 33 centimeters. 0.03 squared. So that's going to be 9. So we start over 0.03 squared. So that's going to be 1, 2, 3, 4, 5, 6. Let's sum 3, which is 9. So 1 times 10 to the 9. It's 10 per Coulomb. Or you can write the whole billion there. Fine. Then Coulomb's law in what? Remember we said with the electrostatic force. The electrostatic force, whether it's attraction or repulsion, between two charges. Between two charges is directly proportional. Directly proportional. The product of the charges, the product of the magnitude of the charges, and inversely proportional. Inversely proportional to the square of the distance between them. Distance between them. Okay, remember I said that is if that is true, then they want us to get the net electrostatic force experienced by point charge C as a result of A. So they want the force because of B and because of A. Okay, so I'll just kind of draw that for my convenience. What is this? Here's the 3 and the 4. Okay, so I need to get the force. I need to calculate the force between A and C. Okay, just for convenience. HA C over R squared. So 9 times 10 to the 9. That is 100 times 10 to the negative 6. 100 times 10 to the negative 6. Distance of separation is 3 and 3, which is 6. So that's going to be 0.06. That's fair. Okay, put that into my machine. Let's 10 to the 9. Let's turn by 100 times 100 that over 0.0. Giving me 25,000. Okay, that is nothing. Since the two are positive charge, then let's consider. Since the 20,000. Then I look at the force in B and say Q over R squared. It's going to be more or less the same thing. So 100 times 10 to the negative 100 times 10 to the negative 6 over 0,0. That is some say that is so that is 100,000. Okay, now when you look at this again, it's 2 to the right. Since it's 1,000, right? Then this is going to be less. Put it up in your right. Now, since the first force and the second force are in the same direction, the net just marginal this is okay. 25,000 plus 10, no, 100,000. So that must give us with 105,000. Yeah, it must. Okay. Then now, question number 5 is what I want. Good. Okay, so we have a negative 3 nanocoulomb. One plus 10 centimeters away from this diagram below. Draw the electric pattern. So positive and negative. Doesn't matter which one. Call positive. That comes first. Yeah. So in this that is that. Fine guys, you can do whatever you want to do. As long as you see the two lines leaving from the positive and from the negative. Okay, so now next we have 5.5. If there is a negative impact, then they want us to draw a force diagram showing the electric forces exerted on O by Q1. So since positive and the positive is going to be repulsed. No. The negative, the positive, so attraction. This will move in the direction. This will move in this direction. Then since it's a positive and negative, the attraction. Okay, now since they want the force diagram on Q2 alone, it's going to be then calculate the net force on Q2 as a result of that. So since we drew our force diagram into the horizontal and the vertical, I need to find those forces. If I can find the net result from this. So force horizontal Q1 over R squared. Okay. And the 3, so it's going to be just 9 times 10 to the 9 times 3 times 10 to the negative 9, then times 2 to the negative. Distance is 10 centimeters, is a mass distance, which is 0.1 second. Yeah. Then I just need to put that into my machine. 9 times 3, and then I'm dividing it by 0.1. 3, 8, 1, 2, 3, 8, Newton. Then the F vertical is over R squared. So 9 times the negative positive That's it. 2 times 10 to the negative 9. This time, 35. 0, 0, 5, 0. Okay, when I put that into the math, over 0,05 squared over 2,16 times 10 to the negative 5 meters. 10. But since the vertical and horizontal, for us to find the net force or the resultant, we said we use the vertical squared plus the horizontal squared. So I do that, square root brackets, then 8,1 times the negative plus 2,1, 10 the negative 5, but squared. Okay, I'm having 2,31. Okay, that is 2,31 times 10, 1, 2, 3, 4, 5, 6, 7, 8, 5. So with the vertical, I'm getting this. With the horizontal, I'm getting this value. I think that's the calculator. Then we need to get the direction. We need to get the direction. So theta must be the 6 times the vertical over the horizontal. We do the substitute, like the 2,1 times 10 to the negative 5 over 8,1 and 10 to the negative 6. Here when you put that, let's 2,3. This is the magnitude of force, then it has to be. Then 5.4, we have an unknown charge R. It is placed 3 meters away from unknown charge. As shown, they are telling us that the charge on R is what we need. Okay? If the net electric field is so remember what we said, for net electric field to be 0, then the electric field from different angles, let's say the electric field this side, then the electric field this side, must working in opposite direction. Can be to the left, can be to the right, as long as the direction is opposite. So we need to get electric field at P, sorry, at X as a result of P. So it takes Q over R squared, 9 times 10 to the 9. The charge is 8 times 10 to the negative 9. Distance is 6 centimeters. Convert that to meters. And then when I put this into my calculator, punch that in the calculator, having 180 tau. Okay, 180 tau meters per Coulomb. Then when I look at this side, the E of X, R of X, that's gonna be big over, call this R over R. So 9 times 10 to the 9, that's R divided by 0.01. So when I try my luck with that, because I want to try again. So 1, I'm having 9 times 10 to the that Then remember what we said, for us to have a net of 0, must have the resistive strength actually in opposite directions. If I do that, this means I take it to happen in the negative direction. Okay, so that says 0 is equal to my 180 tau plus, let's say, negative 9. So move the 180 to the left, or you can transpose that so that I have 9 times 10 to the plus is equal to 180 tau. Divide by 9 times 10 to the third. Divide by 1. And that cancels that. And then my QR divide by 9. So I'm having 2 negative 9. So that can also change to 9. Because taking that right. Alright, so that would be that. Question number almost. Question number 6, they are telling us that two identical spheres, Q1 electron insulating film are placed via same charge 2 mm apart. When Q1 is brought into contact and then moved back to original position, gain the negative 12,15, sorry, 12,5. And the charge on each sphere is this. So, guys, one thing we need to remember is that when spheres are brought into contact, there is going to be equal distribution of charges. Look at the separation. The magnitude of charges has to be the same. So number one, they want us to draw the electric field testing around both spheres after they are touched and separated. So since both things negative, so that if obtain that are the quantity, which means it's just gonna be a case of 1,000. Just remember, the two lines have to be the same. So these have to be centered. See, talking of a negative charge. Okay, that is that. And then 6.2, they're telling us that state the law of conservation of charge. So there are quite a number of ways to tell us the net charge. The net charge of an isolated or in an isolated the net charge is constant or is constant. Or someone can talk about that charges can neither be created, charges can neither be created nor destroyed, nor destroyed. They are just transferred. That's what happens. Transferred from one body to another. Alright, so any one of the two will work for us. They are telling us that an electron of negative, an electron, let's between Q1 and Q2, would the electron move to the left, to the right, or stay in the same position?
Now they're telling us that the electron is flat. And remember we said when there's a repulsion, this area or this region of space would experience force here. Nothing is going to happen to this electron. The forces would be equal but opposite. So gonna say it's the same position. Okay, it may be 7.4, 7.4. Or calculate the magnitude of the electric field due to the charge on sphere at 0.10 millimeters to the right, 10 millimeters to the right. So if we have a point 10 millimeters, what will it be? So E, remember we said take Q over R squared. So K is 9 times 10 to the 9, but we told me K is 7.5. Plus 7.5 times 10 to the negative 9 over the distance, they told us 10 millimeters. When you convert 10 millimeters to meters, it's going to be 0.01 square. Alright, so when I do my magic, having 67, 5,000 Coulomb. Then they are telling us in 6.5 that the questions of all relate to the original charges. 1 and 4 were brought in context given in bold capital letters. What is the magnitude and sign of Q1 and Q4? So when we look at it, Q1, Q1, it's negative 7.5 in Coulomb. So it's a negative 7.5 plus it gained how much? It gained negative 12.5. What does this give us? Negative 10.5, that is 20. No, okay. So it is negative 7.5, gives us 1. We can write it the other way around. Okay. Same with your integer. So it has that much. Then for us to get what is left on this, we can do more or less the same. Where we look at negative 7.5 minus 4.5. Gaining is a plus, C is a minus. When you do that, it is positive. That's alternative number 1. Other alternative is by looking at Q1. Yes. Divided by 2 must give us right there. If you have your Q1 known, it will be just transposing that. So that is negative 25 plus. When you multiply both sides by 2, you're gonna get negative 2. This is 25. So when I move that upside, my is just gonna be 45. Then 6.5.2, they want the force between Q1 and Q2 before they touch. So the force should say Q1, Q2 over R squared, 9 times 10 to the 9, the Q1 is 20. 5. Dividing by the distance, so that's it. 6 millimeters. 6 millimeters 0.3 squared. So when I put that into the dividing by 0.03 squared, having 0.01. So that is the force that I'm having. Force that Q1 is just since the charges are opposite, we tell us about. So Q2 equals to 5. We are looking at the system. We are understand our correct. It would have Q1. And then it's electric field pattern. Balance before the test as such. So remember, before the test, we're having a positive and negative. And then after the test, there was a pause. So now with multiple choices, we can use elimination format before we can get to the correct option. Okay. So we have various options that have been provided as possible answers, the following. Each question has only one correct answer, and we need to choose that correct answer and then write that in our answer book. Okay, so I'll start with question number 1. So which one of the following quantities is the tendency of an object to resist a change to its state of motion? Is it inertia? Is it impulse? Is it momentum or acceleration? So we know that acceleration cannot apply that. Okay, because acceleration is the rate in change of velocity. Momentum is the product of mass and velocity. Impulse, it's something else. So the correct option would be A, which is inertia, the tendency of an object to resist motion from Newton's first law. Okay, then 1.2, we have a ball that is dropped from rest at a height above the concrete floor. Okay, and then they're telling us that this ball strikes the floor and bounces vertically up and down on the same spot on the floor. So the velocity time graph is being drawn for us for the bouncing ball, with the points P, Q, R, S representing the different times during the motion. So this point here will represent the time when the ball was just at that height. And when it is dropped, probably it's moving, and then reaches the floor. Okay, and then it starts to move up. And then at this point, it's probably reaching maximum, because you can see that the velocity is 0 at Q. So probably that's the point where the ball reaches its maximum and then drops down, and then at point R, and so on and so forth. So what are we going to say? At which time does the ball reach its maximum height? After the first upward. Okay, so when you talk of first upward, remember here it's coming down. And then between this point and this point, the ball is going up. And then as it goes up, the velocity decreases. We have in that point where the velocity is 0. So point Q will be our answer, and that is option B. And then 1.3, we have 2 blocks, P and Q of masses M1 and M2, respectively, that are held at rest on a frictionless horizontal floor. Both of them are being compressed with a spring as shown. And so blocks are released and then the spring decides to drop to the floor. Block Q, this one moves to the right with velocity V. What will happen to P? So in normal cases, under the conservation of momentum or impact, we know that the momentum or the impact that Q will have on P would be the same, but just in the opposite direction. So in this case, they are asking us to determine the momentum of P. Okay. Now, since they were held together with a spring, and then the spring was removed, so we expect the reaction to be the same, but just in the opposite direction. So if Q is having M times V as its momentum, so it's M2 times V, then the same should be applicable to P, but in the opposite direction. If this is to the right, then this is going to be to the left. So we expect to have M2V, but to the left. Is there an option like that? M2V to the left. That is option D. Okay, then 1.4, they're telling us that the magnitude of the gravitational force that spheres X and Y exert on each other is F. So from Newton's law of gravitational force, if that is X and then that is Y, if these two are separated with distance R, what happens? So we know that the force is directly proportional to the product of the masses, and then inversely proportional to the square of the distances apart. Now the mass of X is doubled. So instead of us having M, we're gonna have twice M, 1. And then they're telling us the mass of Y and the distance just remain the same. Okay, so which means our new F is gonna be G, and then twice M1, and then M2 over R squared. We can move these 2 in front so that it is a G, M1, M2 over R squared. Okay, so we're seeing that this is representing the F, and it is the same thing that is there. So which means our final result must be 2F, or twice the original force. So remember, the force that X exerts on Y should be the same force that Y exerts on X, but in the opposite direction. Okay. So they're asking us which one of the following combination is correct for the magnitude of the forces that the spheres exert on each other. So remember I said they have to be the same, but currently our force has to be twice the original F. So this and that, which is option D. Then 1.5, hot air balloon, vertically downwards. Is moving vertically downwards at a constant speed. This is in capital letters, okay? So something is happening. So constant speed, so velocity is the same. Assume that the mass of the hot air balloon remains constant. So mass is the same, speed is the same. Okay, which of the following physical quantities associated with the hot air balloon will change during the motion? So is it the weight? They told us the mass must stay the same, so weight cannot. Okay, is it the momentum? Momentum, remember, is mass times velocity. So if the mass is the same and the velocity is the same, this must also be the same. So momentum is out. Is it kinetic energy? We know that kinetic energy is a half mv squared. So if mass and the velocity are the same, which means kinetic energy is also the same. What about potential energy? We know that potential energy is mass, gravitational force, and the height. The mass, gravitation, or acceleration due to gravity, and then the height. So the height will keep on changing. There's no way height is going to stay the same. So it's the potential energy that is going to change during the motion. All right, 1.6, a learner that is standing by the roadside records the frequency of sound waves that were produced by a siren of an ambulance, okay? So the ambulance is moving at a constant velocity, along the rod, and then they drew the graph for us. So the y-axis is representing the detected frequency or the frequency of the listener, and then as time passes. So what we can see is that the graph is below, which means the frequency starts by being low, and then all of a sudden the frequency increases. What does this tell us? So if the frequency of the listener overall increases, which means the ambulance is approaching the learner, or it's moving towards the learner. This approaches the learner. Okay, that is the kind of conclusion you can have. So probably it was moving from a distance and then it comes towards the learner. Okay, so which option of the following, which of the following statements concerning the motion of the ambulance is correct? So the ambulance approaches the learner and then passes the learner. You see, if it's approaching then passes, then we will have another extension where the frequency drops again. Okay, so this is a 1-2 approach. It's either approaching or leaving. Okay, so because of this last statement, I'm nullifying A for now. Okay, then let's look at the second option. It moves away from the learner and then turns and approaches the learner. Moves away. So when it's moving away, the frequency is low. And then when it approaches the learner, the frequency increases. There's some truth in that statement. Let's see, option C. It approaches the learner and then turns and moves away. No, that is not correct, because if it was turning away, then the second part of the graph would be below, or would be lower than the first one. And then moves away from the learner and then stops. This is out. So I'll take option B because it has some bit of truth in it. It moves away and then turns and approaches the learner. So as it's moving away, the frequency is below or less. And then as it's approaching, the frequency that will be observed by the learner will be high. So option B is the correct answer there. And then 1.7, we have two identical spheres, X and Y, that are carrying +2 and then -6 Q respectively. Sphere X experiences a force F to the right, X to the right, when the distance is that, all right. Then the spheres are brought into contact and then return to the original positions. Which one of the following represents the magnitude of electrostatic force that X experiences now? So just like Newton's law of universal gravitation, it's just the same as electrostatic force. Okay, what differs is just that this has a constant of K, not G. Okay, and then in this case, we're going to be talking about charges Q1, Q2 over R squared. Okay, I'm not going to simplify everything. I just need to look at what's going on. So I'll maintain the K, I'll maintain the R squared since those are constants. So this will be a 2 times a 6, okay, which will give me 12K over R squared. So currently, before the spheres touch each other, this is the force that each sphere will exert on each other, okay? Then when spheres are brought into contact with each other, okay, so a +2 and then a -6, the charges are going to combine, and then the resultant charge on each sphere will be divided, or will be a result of division between the sum of the charges. So this would be 4 plus -6, that's going to be -4 divided by 2, which means after the separation, each sphere must be a -2 charge. If the distance is still the same, then you try to look for the force, that is K, Q1, and then Q2. So that's over R squared. So that's a K. That is a K. I'm maintaining the K. Q1 is a 2, my Q2 is a 2 over R squared. So that's going to be 4K over R squared. Remember, this was 12K over R squared. This is 4K over R squared. So this is the new force. This is the original. So which one of the following represents the magnitude of the electrostatic force right now? So when you divide 12 by 4, or when you divide this force by this force, it's going to be 3 times smaller. Okay, so if it is 3 times smaller, which means it's 1 over 3 of the original force. Get this new force, divide by the original force. So the option I'll go with is B. That is 1.7. Okay. Then 1.8 in a circuit diagram below, R1, R2, and R3 are identical resistors. So identical simply means they have the same value and the battery has negligible internal resistance. Okay. What happens to the power that is dissipated by R1? No, they're telling us the power dissipated by R1 is P. Okay. So if the power dissipated by R1 is P, the question is asking us, what happens to the power that is dissipated by R2? Now, if I were to assume that, okay, so I'm saying if I'm to assume, let's say, since they're identical, I can call this 2 ohms, as well as 2 ohms. I can just come up with I can set 10 volts as my voltage there. Just I want to bring about the picture of everything. So the effective resistance within this parallel combination, remember we have 2 resistors, so product over the sum, that's going to be 4 over 4, which is 1 ohm. Okay, that is for the parallel combination. Now, since this parallel combination is going to be in series with R1, I'll plus the 2 ohms, which means my effective resistance is going to be 3 ohms. Then if I want to find the current, because I need the current that is passing through there, current is going to be given as V over R. Okay, so if I have 10 over 3, which will be the same as 3 comma something. Okay, let me just leave it as 10 over 3 ohms. Okay. Then I know that from the formulas of power is given as IV. Okay. Or I can use the combination that has that, because now this 10 over 3 is the current that is flowing through this entire circuit. And it's the same current that is going to pass through the R1. So if I were to look at, do I need the voltage? I can use I squared R. Okay. Let's say I'm looking for the power of R1. So it's going to be 10 over 3 squared times the 2. Just 10 over 3 squared. That's going to be 100 over 9. Okay, and then times 2. That's going to give me, I need a fraction. It's going to give me 200 over 9 watts. Okay, that's the power in this. Then what will be the voltage of R1? Voltage of R1 is going to be 10 over 3 times the 2, which is going to be 20 over 3 volts. But if my original was a 10, then I'll have 10 minus 20 over 3. Okay, 10 minus 20 over 3, which gives me a 10 over 3 volts as well. Okay, so we're saying that this voltage is going to be the voltage of the parallel combination. Okay, Now we have the voltage, we can get the current that is passing through there, or we can directly look for a formula that has voltage, because we know the voltage across R3 is going to be the same voltage across R2, okay? The power formula that combines voltage and resistance, is P is equal to V squared over R, okay? So when I get my voltage, which is 10 over 3 squared, and then I divide it with my R, which is a 2. Let's see. That's going to be 100 over 9, and then I'm dividing it by 2. What do I get? I end up with a 50 over 9. So this is the power in 2. This is the power in 1. So now the question is asking, which one of the following represents the power that is dissipated by R2? Okay, so the question is, how does this, remember, for R1 is the same as P, this P. So how does this relate with this? Okay, how does this 200 over that relate with that? So what I'm gonna do, I'm gonna say if I have 50 over 9, then I divide it by 200, still over 9. I'm getting 1 over 4, okay? So I'm saying 50 over 9 divided by 200 over 9. Then I'm getting 1 over 4. So which means this R2 is a quarter of P. And the correct option is A. So I just had to come up with numbers just to create an idea of what's going on there. Then 1.8, they're telling us that the following is a simplified drawing that represents a DC motor. Okay, so one thing we know about DC motors or AC motors is that they use what we call the Fleming's left-hand rule. Okay, that's the basic thing we need to know. They are asking us, okay, that the diagrams below indicate some changes that we made to the motor. So we can see the north and the south being switched around. And then you can see that the terminals are also being switched around in the second option, and so on and so forth. Okay, what is the question asking for? Which of the changes to the motor above will change the original? Okay, what changes are going to change the original direction of rotation? Okay, so what we need to know is from the original, this is the positive and this is the negative, which means current is going to flow in this sort of direction. Okay, because current flows from the positive towards the negative terminal. We know that the field is from the north to the south pole. Okay. Then if we apply our Fleming's left-hand rule, okay, what is happening? All I can see is that this structure of ours, or this plate of ours, or coil, is going to rotate in which direction? Which direction is this? Okay, this is going to be downwards. So which means it's rotating in the anti-clockwise direction. Okay, if I use my Fleming's, I'm going to end up having something like that. Okay, if this is my force, so this is my thrust of the force, this is the field, and then this is the current. I'm just looking at this part alone. The field, current, then it's going to go down. Okay, once it goes down, then the rotation is going to be anti-clockwise. Okay, So the question is asking us what change, or from the given drawings, which one is not going to be anti-clockwise? In other words, which one is going to be clockwise? So changes were made. If I'm to get the question correct, which of the changes will change the original direction? So we want something that's going to create a clockwise direction, not anti-clockwise. Okay, so let's see from diagram number 1. So current is moving in the same direction, but what has been changed is the polarity of the magnets, that now the field will be moving in that sort of direction. So if I look at, I don't know, I will still just look at this side alone. Okay. Okay, so from our Fleming's left-hand rule again, when I try to twist this kind of thing, okay, so I'm looking at this green line. Does that make sense? Green line, green line. Yes, this is going to be moving upwards. Okay, because current is moving that side. So if I'm to draw more or less the same thing, where this is at 90 to each other, it's going to be moving upwards. It's moving upwards. This is a clockwise direction. Okay. Let's try to look at option number 2. Option number 2, the field is to the right. Current is moving in that sort of direction. Okay. With my Fleming's left-hand rule, let me just look at just this portion. Just this portion. Okay. Current is moving in this direction, and so this one is moving upwards also. So which means it's a clockwise. Okay. Let's look at option number 3. If I focus, current is moving in this sort of direction. If I look at my field, and focus on this, that current is moving in this sort of direction. Okay. Current, where are you? See, your field is moving that way. So it means it's going to move downwards. This one moves downwards, which is the anti-clockwise. Okay, anti-clockwise. So, which of the following changes will change the original? So, number 3 is original. Okay, so 1 and 2 are the changes that are going to change the original direction, since both of them are giving us the clockwise. So 1 and 2, which is option A. And then 1.1.0, 1.10. An atom has a ground state energy, that is X. When the atom moves to a higher energy state, which is Y, there's a line spectrum that is observed. Okay. So one thing we know is that when atoms move, so we're saying if the energy at ground is X and the energy at the higher state level is Y. When that happens, there's an absorption that will take place when atoms move from low energy levels to higher energy levels. That is absorption that is taking place. When they move from high energy levels to low energy levels, that's when they emit their energy. Or that's when they emit light in the form of that. Okay, so our options have to be C and D. Okay, since there is absorptions moving from a low energy level to a high energy level. Then the change in the energy, since this energy is higher than this one, so the change is always highest minus lowest. So Y minus X and then that's the absorption. So I'll go with option D. Okay. If there's any difference, please let us know under the comment section. Okay. Then question number two. Question number two. They're telling us that a block A of mass M is connected. A block of mass M is connected to block B of mass 7.5 kilograms by a light inextensible rope passing over frictionless fluid, as we can see. Okay, we have a height of 1.5 meters above the ground, and so on and so forth. All right, let me just try to decrease this so that we can see the entire question. All right, I think that's much more better. Okay, this is our height, that's all that. All right. So while block B is released, okay, remember, initially it's been held at this point without moving. When B is released, it moves vertically downwards and strikes the ground with 3.41 seconds or meters per second. Okay, if we are ignoring friction, can we show by means of calculation that the magnitude of the acceleration of block B is 3.88 meters per second squared, while the block was moving vertically downwards? So what I can see is that if our focus is on block B alone, then we shall assume something like a free fall in that case, where the motion is entirely under the influence of acceleration due to gravity. It's more like a vertical projectile kind of scenario, okay? And if I'm to look at it in that form, then I'll have to apply those equations of motion, okay? In this case, I could say that, what do I have? I have my displacement. So change in y is 1.5. What else do I have? I have my final velocity, which is 3.41 meters per second. What is our initial velocity? It's a 0. Okay. Is there anything else we need? Is there anything else we have? We want the acceleration. Okay. Projectile. Okay, that's fine. So I can say that if I have v squared, bf squared is equal to v I squared plus 2a delta y. Okay. So I know my final, my initial, I know. Acceleration is what I want. I have my displacement. Okay, so this is going to be 3.41 squared is equal to 0 plus, this is 2 times 1.58. Okay, when I have 3.41 squared, that's going to give me 11.6281 is equal to 3a. Then I'll divide both sides by 3. And then what is my a? My a is 3.876. When I round it off, I'll get 3.88 meters per second squared. Okay, so that is how I would go about answering 2.1. Then when I look at question 2.2, okay, 2.2, they're asking me to draw a labeled free body diagram showing all the forces that are acting on B. So when you look at B, there's just weight that is acting downwards, and then this tension force that is within the rope. Okay, so my free body would be just tension, and then we're saying this is the weight. That is just enough. And then 2.3, can we state Newton's law, Newton's second law of motion in words? Okay, so there are different formats, there are different scenarios to this law, but they are just some keywords that we normally want, okay? And so one can say that the net force that is acting on a body, an object, is directly proportional. Okay, the net force acting on an object is directly proportional to the acceleration. Net force is directly proportional to the acceleration and inversely proportional. Inversely proportional to the mass of the object. The mass of the object. The net force acting on an object is directly proportional to the acceleration and inversely proportional to the mass of an object. Okay. And one thing we know is that this acceleration will always be in the direction of the force, directly proportional to the acceleration and inversely proportional to the mass of the object, and acts in the direction of the object, direction of motion of the object. Okay, just play around with those words, but for as long as we see this word of directly proportional, okay, so that the force is directly proportional to the acceleration. At least it must be within your statement. And then inversely proportional to the mass, and then acts in the direction. So they're just keywords that we're interested in, but play around with the English. Then 2.4, they want us to calculate the value of M. Okay, M is the mass of the second body by applying Newton's second law on each block. Okay, so when I look at my object A, I have tension that will be acting upwards. And I know weight will be acting downwards. So from Newton's second law, we know that F net is equal to MA. Okay. And then when I look at, we're saying body A, my F net is going to be the tension, which, because I'm assuming if the whole direction is moving downwards, whereby B is moving downwards, which means A is going to move upwards. And for A to move upwards, the tension must be slightly greater. Okay, so I'm going to say tension minus the weight of A must give me the mass of A times the acceleration. Okay, I can do my substitution. I don't know my value of the tension, so I'll say weight is given as the product of mass and the gravitational force. So I'll say weight. Why don't I just move everything so that I can make tension the subject, so that I have mass times my acceleration minus my weight, which is going to be mass times the gravitational force. So what is this going to become? Mass is common. I don't know the mass of A. So that's going to be my A, which is 9, sorry, the acceleration that we got, it was 3,88. Okay, that's 3,88. When this one moves that side, it's a plus, sorry, it's not a minus. And then that's 9,8. So guys, I'm factorizing out the mass. I'll be left with the acceleration and then the gravitational force. So which means my tension is going to be, what's 3,88 plus 9,8? I'm getting 13,68, 13,68 M. I'm going to call this equation number 1. Okay. And then when I look at body B, okay, with body B, remember we said the weight from the free body diagram that we drew. Okay, the weight is moving downwards. So which means the weight has to be a bit greater. So we're saying F net is equal to MA. So we're saying the weight minus the tension must give us the mass and the acceleration. And so the weight of B, remember our mass for B was 7.5 times 9.8. From the definition of weight, we said mass and the gravitational force. We are subtracting the tension, which we don't know, should give us the mass, which is 7.5 times 3.88. Okay, so when I simplify, or I can even substitute at this level. Okay, but let me first simplify. I know I have 7.5. Hello, 7.5 times 9.8. That's 73.5. Minus my tension is equal to 7.5 times 3.88. That's giving me 29.1. Okay. I can move the 73.5 to that side. I transpose it. So negative T is going to be the same as 29.1 minus 73.5. When I get 29.1 minus 73.5, I'm getting negative 44. Okay, 4. Divide both sides by negative. So which means our tension is 44.4. Then I'll get this tension and substitute it into origin, the first equation, which means 44.4 is equal to, that was 13.68. 13.68 M. And then I can divide both sides by 13.68, divide by 13.68. Okay, when I do that, I'm getting 3, so my M becomes 3.2456, which is the same as 3.25 kilograms. Okay, so that is that with that question. And then 2.5. So we've answered 2.4, now we're going to 2.5. They want the maximum height above the ground that block A is going to reach. Now, for as long as there's motion and the entire system is moving, the entire system is going to move with the same acceleration of 3.88, because that would have been the other option that we could have used to get 2.4, okay, when you're calculating the M. But since they wanted on each block, that's why we worked it out separately. So with 2.5, since the whole system is using the same acceleration, which means when this block B strikes the ground, okay, that would be the velocity with which block A will also be moving upwards. Now, since block B is going to move 1.5 meters down, we expect block A to also move more or less the same distance up. But because of the 3.41 meters per second, and because of inertia, this body will continue moving upwards till this velocity dies to a 0. Okay? So what we need to know, or what we need to differentiate, is that after the 1.5 height, 1.5 meters height, this body A is still going to continue with the 3.41. Since at that height, body B is halving the 3.41. It's a system, so everything is more or less the same. Okay, so we're going to say at a height of 1.5 meters, at h of 1.5 meters, A will have what we're calling the VI of 3.41 meters per second. And we know that at maximum height, at height maximum, the final velocity must be a 0. Okay, the question is asking us to find the displacement. So we need to find the height that the object moves. Good people, what do you think? What do you think? What do you think? What do you think? So I can use that formula of the VF squared is equal to VI squared plus 2G. If I use G, I can use A. I don't need to use G as such. I can use A delta Y. Okay. When I apply my substitution, we are saying our VF is 0 is equal to the VI, which is 3,01 squared plus 2. Why am I using a plus? It should be minus, since the body A is moving upwards. So I can say plus, then I can use negative 9, what's wrong? Negative 9,8. Will it make sense? Makes sense for me to say that. Use 9,8. Why can't I use my acceleration, which is 3,8? 3,88 delta Y. Okay. Then I can move this to that side. I know that 3.88 times 2 is going to give me 7,76 delta Y, and then 3,41 squared is giving me 11,62. Does that make sense? Guys, I need to change this because remember, after the height of 1,5, this is going to behave as a projectile. So negative 9,8. It cannot be positive, the 3,8, because the system would have stopped moving because of the block B. Okay, so this must change to a 19,6. Okay, because 9,8 times 2, that's 19,6. Then I can divide both sides by 19,6 over 19,6. Okay, when I do that, then my Y is going to be 11,6281 divided by 19.6. That's giving me 0,59. Okay, 0,593. So which means this is the extra distance that the block moves upwards if it reaches the maximum height. Now, since the question is asking for the maximum height above the ground, then we're going to get our 1,5 plus the 0,593. And then that's going to give us 2,093 meters or 2,09 meters. Okay, so that is question number 2. Let's look at question number 3. Number three. We have a ball A that is dropped from rest. Okay, the keyword there, rest, and the height is 15,2 meters high. Then after ball A has fallen, just a small distance of 3,2 meters, a second ball is projected upwards from the ground. And then after a while, the two balls strike the ground at the same time. Okay. Let's see, define the term free fall. So one thing we said about free fall is that this is basically a motion of an object that is entirely under the influence of acceleration due to gravity. And say the motion of an object or motion that is entirely influenced, or that is entirely influenced by acceleration to gravity. That would be my mini description. Okay. Then they're asking us to determine the time that it takes for ball A to strike the ground. So when we look at ball A, what do we know about ball A? Okay, this is 3.2.1. So for ball A, we know that the initial velocity is a 0. The displacement that it must go through is 15.2 meters. Okay, is there any other information that was given? They want us to find the time. Delta T is what we need. We know the final velocity. Oh, we know the final velocity. So, good people, what do you think needs to be done? So when I look at this question, which equation of motion are you going to use? Because V final is equal to V initial plus this won't work. But since we don't have our final velocity, we can use this one, where we look at V initial times time plus a half G times delta T squared. Okay. So our displacement is 15.2. Our initial velocity is 0. So that is going to die out. Since the object is moving downwards, I'll treat it as positive. So that's a half times 9.8 T squared. Okay, so 15.2 is equal to a half of 9.8 is 4.9 T squared. Then I'll divide both sides by 4.9. So 15.2 over 4.9 is equal to T squared. And then I'll take square roots on either sides. So 15.2 over 4.9 gives me that square root of the answer. I'm getting 1.76 seconds. Okay, so that is what they want us to find for 3.2.1. Then 3.9.2, 3.2.2. That's one with me with 9. They want the magnitude of velocity with which B was projected. So guys, what I can see, remember, since we have our time as 1.76 seconds, we need to find out how much time did this object travel a distance of 3.2. And then perhaps if we can subtract that, then we could get the time with which object B is going to travel. Okay, to go up and even come down. Okay, the total time for object B. So I'll say that I'll say this is 3.2.2. Time taken for A to travel 3.2 meters. Okay, so I can still use the same formula of delta Y, delta T plus a half delta T squared multiplied by G. So where there's delta Y, I'll have my 3.2. You say that is a 0 plus, remember object A is going down, so I'll still take my g to be positive. So that is a half times 9,8 delta t squared. Then I'll have 3,2, I'll divide it by 4,9 is equal to t squared. And then I'll take square roots. Okay. So square root of 3,2 over 4,9 is giving me 0,81 seconds. Okay. So this is the time that the object A had traveled just for this small distance. Now, if that is 0,81, then how much time is left for object B? Okay, I'll say time of travel for B is going to be 1,76 minus the 0,81. Okay, 1,76 divided by 0,8, so minus. Okay, so we said 1,76 minus 0,81, and that gives me 0,95. Okay, seconds. Now, remember the question wants the initial velocity for B. Okay? So if this is the time of travel, the total time of travel, I can look at a point where this object goes. I don't know where it ends, no? But then it's going to come back down. So it's saying the total time is the 0,95 seconds. So I'm going to take my displacement at that point. Okay. So my displacement, I'm going to take it as a 0 because it went up with a positive displacement and then it came down to the point of projection. So my displacement is 0. My time is this. I need my initial velocity. So initial velocity is what we want. So from delta y is equal to vi delta t plus a half g delta t squared. Okay, so where there is delta y, I'm saying I'm going to use a 0. Initial velocity is what I need times 0,95 plus, I'm going to say a half times, since the object is moving upwards, then my gravity is going to be negative 9,8, but with a t squared. I simplify this. I'm going to take this, I'm going to move this to that side, to the left, the equal signs. So that's going to be 4,9 t squared is equal to 0,95. What's happening? What's wrong with me? Why am I not replacing t with 0,95? Okay, 0,95 squared. Okay. Then if I simplify this, I have 0,95 times 4,9. Okay, I can just cancel this with just one of these, just quick. So that I have my V initial as 4,655, which is approximately 4,66 meters per second. Okay, so that is that. Or if not, simplify this whole thing with the square and then divide by 0,95. You get the same thing. All right. Then the next question is telling us that on the same system of axes, can we draw a position time graph to show the motions of ball A as well as ball B? After time it was dropped and reaches the ground. We're taking the ground to be the 0 position. We need to label the graphs A and B, and we need to indicate the following. So there is one thing we need to know. Let's see. With the initial velocity of 4,66, how far is the object going to go? Let's say I'm looking for the maximum height. So delta y is equal to vi delta t plus a half. That makes sense. Let me use v squared is equal to v initial plus 2g delta y. Okay, so my final is 0. That's 4,66 squared plus 2 times negative 9,8 delta y. So 4,66 squared gives me 21,716. It's going to be equal to 19,6. So 19,6 delta y. And I divide both sides, 21 divided by 19.6. I'm ending up with a very miserable answer, guys. 4.66 squared. Okay, that is 21. So which means this object is going to move just a small height and then it drops back. So which means it's not going to go beyond the 15,2. That's what I was looking for. So if this is our position, I can say delta y in meters. This is our time in seconds. So if this is my 15,2, this object is just going to move to that point. So if this is our time that we said it was 1,76. The second body, I'll call this A. Body B, we said starts at 0,81 seconds. It moves up, reaches its maximum, and then falls back within the same sort of time. Then I'll call this my B. So guys, this is how the graph for 3.3 would look like, according to me, guys, no? According to my understanding of the question. Then let's look at question number 4. So question 4 is telling us that trolley A that is having this mass moves 0,4 meters per second to the right in a straight line on a horizontal front, collides with a stationary. So if the velocity is 0,4 meters per second, which means the initial velocity here is 0, then after the collision, they're telling us that the trolley is locked together. In other words, they move as a combined body to the right. State the principle of conservation of linear momentum in words. So what we know about conservation, we can say that in an isolated system, okay, we can say that the total linear momentum, what is spelling of momentum? It's constant. So what that means that it stays the same. Total linear momentum before collision is the same as that after collision. Then 4.2, they want us to put the magnitude of the velocity of the trolleys immediately after the collision. So from the law of conservation, we know that mass A, velocity initial of A, plus the mass of B times the velocity initial of B must give us the velocity combined of mass A plus mass B, since they're going to have the same velocity after a collision. So the mass of the body A was 7,2. This is 7,2 times the initial velocity, we told us is 0,4. Plus, we know that the mass is 5,3 there, times the velocity 0 is equal to V into 7,2 plus 5,3. So we know that 7,2 times 0,4 is going to give us 2,88. We know this is a 0, so on my left I'll have 2,88, and then 7,2 plus 5,3, that's a 12,5 velocity. And I'll divide both sides. by 12,5, divide by 12,5. So this cancels that. And then my velocity is going to be, what is it? I'm having 0.23, 0.2304. So just 0.23 meters per second. 0.23 meters per second. So that is the velocity of the combined, okay, 0.23 meters per second. Then 4.2.2, they want the average net force exerted by A on B during the collision. If the collision time or the time of contact is 0.02 seconds. Okay, so remember, they want the average net force. Average net force. So we know that F net is the same as mass times the acceleration. Do we know the acceleration? No. You can say that acceleration is the same as the rate in change in velocity. Okay. So which means it's M, which is V final minus V initial over delta T. Or someone can look at it as the net force being the change in momentum. Okay, the change in momentum, so that it is F times T is equal to that. Then what we say from this, we know that our mass, we're going to use the mass of B, which is 5,3. The final velocity that we got was 0.23. The initial velocity of B was 0 since it was stationary over the 0.02. So when I substitute that into my calculator, this is 0.23 minus 0. Let's say 0, no, okay, over 0.02. The answer that I'm getting is 60.95. This is force, which means it will be measured in newtons. Guys, that is question number 4. Let's look at question number 5. Number 5, they're telling us that we have an electric motor that pulls a 20 kg crate from rest at point A up an incline by means of an inextensible rope. The inclined plane makes an angle of 80 degrees with the horizontal. We have B, C, and D are points on the incline, and the distance between A and C is 15.6. Then the motor exerts a force. Okay, this is important. So which means like the force applied is 96.8. And then there's a frictional force of 13.5. It's constant. Okay, define a non-conservative force. So we know that a non-conservative force is one where the work done, okay, is dependent, where the work done, let's say, depends on the path is taken by that force. Is a force where the work done depends on the path. Remember, for a conservative, it's independent. All right, then 5.2. 5.2, use the energy principles to calculate the speed of the crate when it reaches point C. So what I see is that, let's say this crate is somewhere there at point C. What forces will be acting on this crate? I can see the force applied. I just want the forces that are acting along the incline. And since it was moving upwards, then there's a frictional force somewhere there. And then there's also the FG parallel that will be acting along the incline as well. So since we say the work done depends on the path, I can try to look for the work done by each individual forces. And that work done, remember, is equal to the change in the kinetic energy. Okay, we know that work done is the force times the displacement, and then the cos of z, or the cos of it in that case. So what I'm going to do, I'm going to say work done, or the net work is going to be F delta X, and then the cos of Z. Okay, but remember, this is our F net. Let's get the F net. F net, since the what? I'm going to have the 96. Why don't I just call it the force applied first? Okay. Plus, we can see the frictional force that is acting in the opposite direction. And then plus the FG parallel that is also acting in the opposite direction. Okay, so I'll just attach the negative signs just because they are working in the opposite direction. So this is 96,8. Okay. Minus, they say the frictional force was 13,5. I'm not changing that. Okay. And then minus FG parallel. Remember, FG parallel is given as mg, the sine of the angle of inclination, which is 18 in this case. So it's going to be 20 times 9,8 multiplied by the sine of 18. I'm just looking for the F net. When I punch this into my calculator, 733 times my delta x. Remember, delta x is the displacement, which is 15,6. And then I'll say the cos of 0, since it's acting in the direction of motion. Okay, so I'll multiply this times 15,6. That's gonna give me 354,63 if I'm to round it off. Okay, these are joules. But we're saying net work done is equal to the change in kinetic energy. So initially, the question was specific and told us that the initial velocity was at rest or 0. Okay, where is that statement? So the constant and that, the mutex, that's this, and that's when it reaches C. Okay, so which means I'm gonna have my 354,63 is equal to a half m, that is V final minus V initial, that's squared. Okay, so that's gonna be, what am I looking for? I'm looking for the velocity. So 354,63 is equal to a half times 20. Remember, my final velocity is what I'm looking for. Initial velocity is 0. So that's going to be V final squared. So that is 354,63. When I multiply a half of 20, is going to be 10. Divide both sides, I have my VF squared, and then I'll find my square root. All right, so the square root of 85,463 is giving me 5,955. 5,955 which is approximately 5.96 meters per second. Okay, so that is what I'm getting. 54 to 5.96 meters per second. Okay, so guys, that's what we have. Then we look at the next question. They're telling us that when the crate reaches point C, the rock breaks. Okay, the crate continues moving up the inclined plane, and then it comes to a stop at point D. Okay, so at point D, the crate has stopped moving. Then the question is asking us, after stopping to move, it slides down past point B. They want us to draw a label diagram of this crate when it is moving down at point B. Okay, so at this point B, if it's moving downwards, remember there will be no longer the applied force. So what will be affecting this will be the frictional force and the FG parallel. Okay, this side, no, it's just the FG parallel that will be acting downwards, and the frictional force will be acting upwards. We shall have the normal force and then the FG perpendicular in that manner. So which means my free body diagram is going to have my frictional force. This is the FG parallel. We can have the FG perpendicular, then the normal force Fn. So just that, how many marks is it? Question is 3 marks for 4 forces. It's reasonable. Then 5.5, they want us to draw a velocity time graph for the entire motion of the crate. So what I can see, okay, is that the initial velocity of the crate was 0 before it started pulling or being pulled. Then it reached a maximum of, we said 5.96. Okay. And then from there, the block continued slowing down. Okay, this is going to be velocity in meters per second. Okay, it slowed down and it got to a point, probably D, where the final velocity was a 0. And then it started dropping or coming down, sliding downwards. So remember, this must be straight lines, but this doesn't look like it. Okay, so I'm just going to draw straight line. So we're saying this point is the point D, where the velocity is 0. After it snapped, it continued a little bit till the final velocity was 0, and then it came down. All right, so what do they want us to do for the entire motion until it passes point D, again on its motion down the incline? So you can just extend this limits. There's no harm in that. This was time in seconds. Okay, guys, I think that's that. Question number 6. Question number 6. A car is moving at a constant velocity of 20 meters per second on a horizontal road towards a stationary device, which can both emit and detect sound waves. The device emits. Okay, so this is the frequency of the source. Waves that are reflected off the car and then they are detected by the device. Define Doppler effect or state Doppler effects in words. So we know that Doppler, it does skip a question, guys. It does skip a question. That's 5.5, no? Yeah, remember scripting question. So okay, so it's saying Doppler effect. Doppler effect. What is Doppler effect? Doppler effect. Doppler effect. Doppler effect. Okay, so we say is the apparent change. Doppler effect is the apparent change within the frequency. Okay? Apparent change within the frequency of the source. Frequency of the source when there is relative motion. When there is relative motion, relative motion, not motive, relative motion between the source, okay, between the source and then the observer. Okay, something like that. Apparent change. Okay, assume the change when there is relative motion between the observer and then the listener. Sorry, observer and the source, because listener is the same as observer. Okay, then 6.1.2, they're telling us that if the speed of sound is 340, calculate the frequency of the reflected waves detected by the device. Okay. This question is 6 months, guys. Because when you look at it, frequency of the listener, something is fishy here. Okay. Let's see if we can break it down. Because 6 marks for was frequency of the listener from the formula. You know that it's V plus minus velocity of the listener over V plus minus velocity of the source times the frequency of the source. Okay. Let's see. So we know that the frequency of the source is 24,000 hertz. Then the velocity of the source is 0. Frequency of the listener, we don't know it as yet. Then we need to find what's gonna be the velocity of the listener. We said it's 22 meters per second. And then our fee is 340. Okay, let's first find the frequency that the person in the car is gonna observe. So from FL, we have V plus minus, we said VL over V plus minus PS times Fs. Now, since the listener is approaching the source, then we expect the frequency to increase, which means we're going to have a plus on top and then minus down. So that's going to be 340 plus frequency of the listener. Sorry, the velocity of the listener is 22 over 340. That's minus 0 times the frequency of the source, which is 24,000. Okay. This looks to be for 6 months, which means there's something else that needs to be done as well. Okay, I have that multiplied by 24,000. I'm getting to 552.94 hertz. I can write this in certain notation. There's no problem in that. 2,94 hertz. Okay. So that is the frequency that the listener is going to observe. But what is the question asking for? Calculate the frequency of the reflected sound detected by the device. So which means when this frequency is reflected, now the car acts as the source. Okay, so which means the frequency of the source is 25552,94 hertz. Now we want the frequency that is detected by the device. Okay, we know that the velocity is still 22, that is velocity of the source. Okay, velocity of the listener is going to be 0 now. Then we do the same thing, apply V plus minus VL over V plus minus Vs times the frequency of the source. So that is 340. Listener is going to be 0 since the difference is not moving. And then that's going to be 340 minus 22 times 25552,94. So 340 over 318 times 25552,94. Okay, 340 over 318 times 25552,94. Is it going to make sense though? Let me try and lift two decimals. Doesn't going to make sense. So I'm having 27320,75 hertz. Okay, so this becomes the frequency that they want, that the machine detects, because there's a bouncing of, which means there is a trip of 2. There's going, and then this coming back. Okay, then 6.2. They're telling us that the spectral lines observed from a distant star will show that the star is moving away from the Earth. Explain by referring to the frequency how one can deduce that the star is moving away from the Earth. Okay, so one thing you need to know is that when the star moves away, the distance increases. In other words, the wavelength increases as the star moves away. The star moves away. And one thing we also know is that from V is equal to F lambda, we know that our frequency is inversely proportional to the wavelength. So what we can say is that as the wavelength increases, okay, the frequency decreases, or the frequency decreases. So what does this mean? It simply means that there's going to be a redshift. There is what we call a redshift, where the lines, or the spectral lines will move towards the red, the orange, and the yellow kind of thing. So that's what we call a redshift. So talk about the wavelength increasing and then the frequency decreasing, since the wavelength is inversely proportional. So we can just say wavelength or frequency is inversely proportional to wavelength. We don't need this, and just use this. Okay. and then just draw a conclusion. So there's a redshift towards the smaller frequency. Okay, then question number 7. Question number 7. They're telling us that 2-point charges X and Y are held at 0.03 meters apart as shown on the diagram. Then the charge X is this, Y is that. State Coulomb's law in words. So that is 7.1. 7.1, Coulomb's law. Coulomb's law, Coulomb's law. Okay. Okay, so we know that for any 2-point charges that are placed next to each other, the product, okay, or we can say that the force between the charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance apart. That is Coulomb's law. That the force between any 2 charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the same product of the charges Q1, Q2 over the square of the distance of separation. You know that when that is removed, then you have your Q1, Q2 divided by R squared, where K is a constant. Remember, it's 9 times 10 to the positive 9. Okay. Then they want us to draw the net electric field pattern due to the 2-point charges. So what we can see is that the magnitudes are the same, 7.2 and 7.2, as much as the signs are completely different. Okay. So I'll say I have my negative there, and then I have my positive. So from Coulomb's law, we know that like charges will repel, and then unlike charges will attract. Okay, just draw the line. What's wrong with me? Why is it moving in that direction? So the field lines must be seen to move from the positive up to the negative charge. Okay, we can have this, that, and then remember, these field lines should not touch or should not cross each other. The lines must be seen. I can add another line somewhere. So remember, since the magnitudes are the same, which means the number of field lines leaving one must be the same as number of field lines that are reaching other. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, something like that. That is 7.2. Then 7.3, they want us to get the force, electrostatic force that Y exerts on X. Remember, this force has to be the same as the one that X exerts on Y. It's just the directions that will be opposite. So we know that the electrostatic force is K times Q1, Q2 over R squared. So we say that is 9 times 10 to the 9. The first Q1 is 7.2. Don't need to really stress about the sign. That's -9. And that's 7.2 times 10 to the -9. I'm dividing this by my distance of separation, which is 0.03, but squared. Okay. So when I punch this into my machine, 7.2 times 10 to the -9 times 10 to the -9 over 0.03 squared. Okay, I'm having 5.18 times 10 to the -4. Okay, since this is a force, so we can say in newtons. Now someone will talk about the direction. magnitude that force y results in x. It's not a big deal. So that is the magnitude of the force. Then 7.4 has information that a third point charge Z with unknown positive charge. So which means there's a positive charge somewhere there. It's positioned that point X on the line. All right. Can we draw a labeled vector diagram showing the directions of the electric fields at a point X, at a point where X is positioned? So all we can see is that the electric field as a result of this is going to act in that direction. And then in this case, it's going to act in that direction. Since the signs are opposite, so there has to be attraction. Okay. So that, then it's going to be that. I can call this E, the result of XY, E as a result of XZ, or EZ and E. It's okay. No problem. So that has to be our vector there. Then 7.5, they're telling us that the magnitude of the resultant electric field. Okay. Remember, electric field is given as KQ over R squared. Okay, so I need to first of all get, we need the magnitude of Z. So we're gonna get the electric field in this direction, and then the electric field in this direction also. So I'll say the electric field, EXZ, it's gonna be KQ over R squared. So which is 9 times 10 to the 9 times my Q here, which is gonna be a Z over 0.01, that's squared. Okay, so that's 9 times 10 to the 9 over 0.01 squared. That is giving me 9 times 10 to the 13Z. Okay. And then when I look at the electric field, XY, it's going to be the same. The Q that I'm using is the Y. The Q that I'm using is the Z over R squared. So 9 times 10 to the 9 times, we say 7.2 times 10 to the negative 9 over 0.03 squared. Okay, when I punch this into the calculator, 7.2 times 10 to the negative 9 over 0.03. I'm having 7.2 times 10 to the 4. Okay. But now they are acting in opposite directions. Okay. So one is going to be positive, one is going to be negative. So we're saying E net is going to be EXZ, okay, plus the EXY. Let me try to do my substitution into the formula so that I can see what I get. So they gave us the net as 4.91 times 10 to the 5. EXZ is 9 times 10 to the 13Z plus, this is going to be negative 7.2 times 10 to the 4 XY. All right, then I'm going to move this to that side. I'll move that to that side. So that's going to be 4.91 times 10 to the 5 plus 7.2 times 10 to the 4 is equal to 9 times 10 to the 13Z. And I simplify the 4.91 times 10 to the 5 Okay, but I'm adding the 7,2 times 10 to the 4. That's giving me 5,63 times 10 to the 5. I'm dividing this by 9 times 10 to the 13. So what is my Z? 9 times 10 to the 13. That gives me 6,25555. So that's 6,26, I think, times 10 to the negative 9. But since it's a charge, so we can call it coulombs. Or someone can call it 6,26 coulombs. No problem. No problem. Question 8. Question 8. They're telling us that a battery of some unknown EMF and some unknown internal resistance. So we don't know this, and we don't know the internal resistance as well. It's connected to 3 resistors and a high resistance voltage, 2 switches and 2 ammeters of negligible resistance. All right. They want us to state Ohm's law in words. They want us to state Ohm's law in words. So with Ohm's law, all we need to know is that the potential difference across a conductor, potential difference across a conductor is directly proportional to what? To the current. Okay, but at a constant, the current across the same conductor at a constant temperature, not a constant temperature. So that is Ohm's law. Then if both switch S1 and S2 are closed, the ammeter reading A1 is 1,5. Can we get the reading of the voltmeter? Okay. So what I'm gonna do, since this and that are in series, I can combine this so that I have a total of 7 ohms. Okay. So the current through this is going to be 1,5. So I can say that the resistance, let me just say 8.2.1. The resistance at the bottom is going to be 2 plus 5, which we are getting as 7 ohms. And then the current is 1,5. We can get the voltage. V is equal to IR. And that is going to be 1,5 times 7. What is the question asking for? We want the voltmeter reading. So we need to get the voltage across. 1,5 times 7, I'm having 10,5 volts. So this must be the voltmeter reading. And then 8.2.2, they want us to get the reading on the ammeter, 18. So this ammeter reads the total current that is passing through the circuit. Okay. Now we know that this 7 ohm, if we combine these two and we get one single equivalent resistor, the 7 ohm and the 3 ohm are going to be in parallel. Okay. So since we know our voltage as 10,5 across, we need to get the effective resistance of the circuit. Okay. So effective resistance, I don't know, someone can get the effective resistance, but why should I go the long way? I feel like that is a long way. I know I don't need to combine. The voltage across a parallel combination is the same. So 10,5 is across this, 10,5 is across the 3 ohm. Why can't I just get the current? Okay. So I'll say from Ohm's law or from the Ohm's formula, V is equal to IR. The current across the 3 ohm is going to be 10,5 divided by 3. 10,5 divided by 3, which is 3,5. And then the total current through here is not the same as 1,5. So 1,5 comes when I combine the two, I'll get my total current. So it's saying 3,5 plus 1,5, which gives us the 5 amps. Okay, 5 amps. I feel this is shorter. And as much as someone that finds the effective resistance, okay, effective resistance within the power combination of 3 and 7, remember it's the product and the sum. So product over the sum, which will be 21 over 10. When the voltage is still the same, so the current is going to be voltage over resistance, which is 10,5 divided by 21 over 10. And simplify that, we should be able to get 21 over 10. Okay, it also gives us 5. Okay, so whichever way, so this is a bit long. This is quite cheap and quick. All right, so whichever option you choose, guys, for as long as we get the same answer, okay? Then 8.2.3. They are asking for the power that is dissipated within the 3 ohm resistor. Power dissipated within the 3 ohm resistor. Now, since we have the current of the 3 ohm, okay, the same current within the 3 ohm, we got it as 3.5. We have our resistance as 3. All we need is the formula of power, the equation of power that has current and resistance. Formula of power with current and resistance is I squared R. So which means it's going to be 3,5 squared, okay, times my 3. So when I simplify that, that is 3,5 squared times 3. I'm getting 36,75 watts. Alternatively, I can use the voltage approach where I have V squared over R, because you know the voltage across the 3 ohm is 10,5. Okay, and then I'll divide by 3. 10,5 squared divide by 3, I'll still get the same thing of 36,75 watts. So whichever option you take to use, we shall be happy for you. So that is 8.2.3. Then we move on to the next condition. S1 is open. Okay, so if S1 is open, which means our main focus is just the 3 ohm. Means S, wait, which one is open and which one is closed? S2 is opened. S2 is opened. So which means S1 is closed, and we shall have just the 2 ohm and then the 5 ohm. So they're asking us to calculate. No, skip the question, guys. Sorry. S1 is opened while S2 remains closed. The reading of the ammeter changes to 3,64. Can you calculate the EMF? Okay. If S1 is open, which means these 2 resistors are out, we're just focusing on the 3 ohm. And the current through will be 3,64. So I feel there is a simultaneous that we can solve. Okay, this is 8,3. From the EMF formula, we know that it's current into capital R plus the small r. Okay, we don't know the value of the small r and all of that. So Initially, okay, initially, our EMF would have been, we say the current, the total current that is passing through the circuit. What answer do you get for 8.2.2? 8.2.2.5. So that's going to be 5 into the effective resistance for the total circuit. Remember, this is a 3, that is a 7 combined. So the product is 3 times 7 over 3 plus 7, which is 21 over 10. 21 divided by 10 is going to be 2,1. Let me just use it as 2,1 plus R. I can simplify this further so that my EMF is going to be 2,1. 2,1 times 5. That gives us 10,5 plus 5R. I can call this equation number 1. And then now when I look at the condition that I've been given, the ammeter reading changes to that. So which means my EMF currently now, the EMF, the current is 3,64. The total resistance, so the resistance external is going to be just 3 ohms plus R. Open this up. I'm going to have 3,64 times 3, having 10,92 plus 3,64R. I can call this my equation number 2. Since the EMF is the same, I can equate equation 1 and equation 2. So that my 10,5 plus 5R is equal to 10,92 plus 3,64 small r. Let me move the r's this side, let me move the constant that side. So 5 minus 3,64 is going to give me 1,36R. And then 10,92, when I subtract 10, plus 3,64 times 0,309, I'm having 12,04 volts. 12,04. Our focus is now the 7 ohm combination. They're asking us, how does the voltmeter reading change? We need to choose increase, decrease, or remains the same. Okay, so what I can see is that looking at the combination, this was in parallel. Okay, and we got the effective resistance to be 2,1. Now, if we remove the 3 ohm, the effective resistance is now going to be 7. In other words, the resistance external is going to be 7 ohms. So what I'm seeing is that 1, resistance is going to increase. Okay, the resistance is going to increase. And if resistance increases, what happens to the current? The current through the circuit decreases. Okay, which means the V external is going to decrease. But then the V internal, which means the IR, must increase to make sure that the voltage across or the EMF is maintained. So if the internal voltage increases, which means even the voltmeter reading is going to increase. Since remember, the voltmeter is connected across the battery source. Okay, let's answer the question. So say This is 8.4. 8.4, so it's saying it's gonna increase. Reason being that opening S2, you can say just cuts off the 3 ohm, hence increasing the resistance external, and this decreases the current in the circuit. Okay. Therefore, the V external will decrease, but then the V internal will increase. That's the increase in the voltmeter reading. That's the increase in the voltmeter reading. All right. Question number 9. They are telling us that the simplified sketch below represents an AC generator. So guys, remember, before we move forward, motors use the Fleming's left-hand rule. Before I forget, this is motors. Generators, they use the right-hand rule. Fleming's right-hand rule. Okay, with a coil that was initially horizontal between the poles of the magnet, X and Y are 2 points on the coil, YA is one of the poles of the magnet. All right. So the question is asking us that when the coil of the generator rotates clockwise, just as indicated, between the 2 poles, the direction of the induced current is from X to Y, okay, as shown above. Is A the North Pole or the South Pole? So remember what we did when we were looking at the multiple choice question. So if I focus on this and I apply my Fleming's right-hand rule, okay, I look at the current moving that side, and then the direction is upwards, which means my force is going to be moving in this sort of direction. Okay, so since this is an AC generator, this is going to be our EMF measured in volts, and this can be the time in seconds. Since it's EMF, time graph for 2 complete rotations. But they are telling us that we must start from the position of the coil as shown. Okay, so when the coil is horizontal, that's when we experience the maximum EMF. Okay, so what I'm gonna have is something like this. Okay, that is one rotation. And then I'm gonna have another rotation, something like that. So that would be my EMF time graph. In the 9.2, they're telling me that an electrical device is connected to the AC generator, and then the root mean square potential difference across is 200 volts. So RMS is 200 V. Okay. And then the maximum current. Okay. Current maximum is 6 amps. What does the question want? They want us to get the resistance of the device. So before we get the resistance, I need to change this maximum current to the root mean square current. So IRMS is going to be the same as 6 over root 2. Okay, since we know that I max is the same as I RMS over root 2. Then from Ohm's law, V is equal to IR. Since I'm looking for resistance, it's the voltage over the current. So it's V RMS over the I RMS. So 200 divided by 6 over root 2. When I punch this into my calculator, 200, not 2000, okay, over 6. And that's the root 2. I'm having 47.14 ohms. Okay, that is 9.2.1. Then 9.2.2. 9.2.2. They want us to get the energy that is consumed. Energy that is consumed by the device in a time of 2 hours. So time is 2 hours. We need to change these 2 hours to seconds. That's 2 times 60 minutes times 60. Okay, what we get? That is 7.2 seconds. From the formula of power, we know that power will be the work done over the time. The work done over the time. Okay. What do we have? What do we have? We have the power, current, and the voltage. We can use that. We want the energy. Okay, so one thing we know is that it will be the energy divided by the delta time, because we know that work done over time, we know that work depends on the energy. Okay, because under the definitions of energy, we will tell you that it's the ability to do work. That's why then the units are usually the same. So I'm gonna just put it that way, so that for me to get my energy, I'll get my power times delta T. So since I have my voltage and then I have my current, I also have my resistance, I can use any of it. So I'll prefer to use the IV and then delta T. So the current that I'm using is the root mean square RMS. So that is 6 over root 2 times the 200 for the voltage from the previous question. That's what we stated. Okay. And then I'm multiplying this by my time. We said it's 7.2. So simplifying this, root 2, okay, that's times 200, and then times 7.2. I'm getting something weird. Okay, getting something weird. Let me just punch it again. Okay, so my weird answer is 6.11 times 10 to the 6 joules. Okay, 6.11 times 10 to the 6 joules. So guys, that is question number 9. Let's move on to question number 10, which is photoelectric effect. So in an investigation of photoelectric light of different frequencies was radiated on each of the two metals, we have A and B. Then the graph of maximum kinetic energy of the ejected electrons from metal A and the frequency of the incident photons is shown. This is the energy. And then that is that frequencies times 10 to the 14. Then 10.1, they want us to write down the numerical value of the gradient of the graph. So it's a 1-mark question, which means it's kind of direct. So in any graph of photoelectric effect, the constant, which is the gradient in this case, is what we call the Planck's constant. Okay, And Planck's constant is usually given as 6,63 times 10 to the negative 34 units. Okay, 6,63 times 10 to the negative 34. That is the gradient. Then 10.2, they want us to define what work function is. Work function is basically the minimum energy. Okay, the minimum energy that is required. Minimum energy that an electron in the metal needs. Minimum energy that an electron in the metal needs. Okay, or the minimum energy that a metal needs for an electron to be moved off its surface. I don't know, that's better. Remember, work function is just the minimum energy, the minimum work that must be done to remove an electron from a metal surface. So whichever way you put it, but there has to be minimum involved. Minimum energy that is needed. Minimum energy needed to remove an electron from a metal surface. Okay. Then 10.3.1, they want us to get the work function of A. So usually where the graph starts from along the horizontal axis, that represents the minimum frequency, or the frequency of the work function. So we know that work function W naught is given as H times frequency naught, because this 5 represents our frequency naught. So Planck's constant is 6,63 times 10 to the negative 34. Then we are multiplying this by, and so we're multiplying by 5 times 10 to the 14. Is that true? Yes. Okay, so what I'm going to do is just punch this into my calculator. 6,63 times 10 to the negative 34. I'm multiplying this by 5 times 10 to the 14. I'm having a weird answer, guys. Again, which is 3,32 times 10 to the 19, but negative. That will be joules, since it's work function, work done. Okay, so guys, we're done with oh, we're not done. They told us the work function. Okay, so we got the work function as 3,315 times 10 to the negative 19 joules. We know that our E is going to be H multiplied by the frequency is equal to the work function plus the EK max. Okay, so at the point of EK max, where we need our E, we can see that the frequency is 12,54. So I'm going to say 6,63 times 10 to the negative 34 times the 12,54 times 10 to the 14 is equal to our work function, which is 3,315 times 10 to the negative 19 plus the EK that we want. Okay, then we multiply on the left. I'm getting something like 8,314 times 10 to the negative 19 is equal to 3,315 times 10 to the negative 19 plus the EK. Then I can move this that side, and then I'll subtract. Okay. When I insert this into the machines, 8,314 times 10 to the negative. Okay, what's happening? Saying 8,31. We said 1414 times 10 to the negative 19. Okay, we're subtracting 3,315 times 10 to the negative 19. That becomes 4, having 4,999 times 10 to the negative 19. So if I round these two decimals, it's just going to be 5 times 10 to the negative 19 joules. We're looking for kinetic energy. Okay, then the next question. The next question, which is going to be 10.4. 10.4. 10.4. Okay, so 10.4, how will each of the following be affected if the light of the frequency 12,54 times 10 to the 14 hertz, but of a higher intensity? So we're using the same sort of frequency light, but the intensity is the one that changes. Okay, how will this have an effect on the value of X? So now one thing we need to know that under the factors that influence kinetic energy, intensity is not one of them. Okay, so in this case, it's just going to be the same. The kinetic energy is going to be the same. It has no effect on the intensity, or kinetic energy is not affected by intensity of the light. And then 10.4.2, how about the number of photoelectrons emitted per unit time? So this will increase. Okay, these are going to increase because as the intensity increases, which means the number of photons that are being released will also increase. Then 10, they are telling us that metal B has a larger work function than metal A. It has a larger metal function. It has a larger work function than metal A. Can you redraw the graph above in answer book, not include values? On the same set, sketch the graph of B and label this. So one thing we know that one thing that we discussed before, we said work function is directly proportional. Okay, said work function is directly proportional to the frequency. So if the frequency is high, which means even the work function is going to be high. And then if the frequency is small, which means even the work function is going to be lower. So from the graphs, okay, I don't need to draw. I'll just maybe just use this. If this is our graph A, okay, with this sort of work function, the graph B has a higher work function, which means it must be drawn somewhere there. And then we call this a B, because let's say if this is a frequency, if this frequency is high, which means even the work function is going to be high. So in your drawing, in your answer book, all you needed to do is just draw something like that and draw something like that. Call that A and call that B. So this is the frequency of A, and then this is the frequency of B. So guys, that's what we had to do, and that is what will be expected of us. So thank you very much for watching. Let's meet in the next paper. Thank you. Hello, welcome to this episode where we shall be talking about physical sciences, paper 1, the May-June 2023. The paper was out of 150 and the duration was 3 hours. Okay, the instructions will always be the same. The paper is having 10 questions.